I'll put the document up and ready. So it's a lot of it is going to be simple math and conceptual stuff right now. All right, so notice that when there's lightning or spark, distance matters, right? All right, he's charging up his body through friction. All right, so now he's charged up either positively or negatively. And the spark is going to happen. His body is charged. This guy is actually neutral. So what happens is this guy's skin is going to become polarized. And only at a given distance, you will see the spark. It's usually about an inch or less than an inch. All right, so that's what you're looking at. So why is it that the spark is not happening when it's like 1 foot away or 2 feet away? And it happens just right there. Why does it happen like right there? So what determines, in terms of the distance, when the spark occurs? All right, so that's what we're going to investigate. Same question. High ground versus the low ground. Which one is more likely to be struck by lightning? You know it's the high ground, right? And you kind of know the answer, reason as to why, because the distance between opposite charged regions is smaller. So smaller the gap is, the more likely it becomes for the lightning to occur within that region. But the thing of it is, if that logic is so correct, why is it that the tallest structures in cities are not the ones that get struck by lightning 100% of the time? And all of a sudden you realize that your explanation, though it's a good one, it doesn't work 100% of the time. So the question is, why not? One of the signs that you're about to be struck by lightning is the hair rising up. All right, so beautiful smile. Her brother thought that this was funny, so they snapped a picture shortly after they left. Lightning struck, one person died, a couple of people got injured. Okay, so the question is, why is it that her hair is rising up? What's causing that to happen?
The negative particles in her hair strands are repelling.
All right, so give yourself 5 points for that one. Okay, so that's a good theory. We'll check to see if that kind of makes sense.
In Glenview, high winds.
This is the one that we keep going back to, and we will keep going back to this one.
Trapping a woman
obviously this week, next week.
Inside her car. Police did not know if the wire was live, so they ordered the woman to stay inside the car to avoid contact with the ground. Then they shut down the entire intersection.
All right, so let's get back to this one. Live wire, touching the car, and then touching the ground. So which means that this car is part of the circuit. This car is completely electrified. In fact, if you were to start walking towards this car, before you reach the car, you would probably go down. You will get electrocuted. It could potentially kill you. You don't even need to touch the car. Start walking towards it. Immediately you will get shot. Okay, so this is a dangerous situation. She's inside, she's fine. All right, your first thought was because of the tires. Tires got nothing to do with it. Why not? Because once the wire goes up and touches the metal of the car and then touches the ground, this becomes a complete circuit. Tires will not get in the way. You're bypassing the tires. Your second thought was she wasn't touching the metal on the inside. She can touch the metal inside. She's still fine. All right, she can touch the metal inside. She can lick the metal inside. She's still fine. Okay, so we provided an explanation for that last time while we were discussing the Gauss's law, because the net charge on the inside is going to be zero, guys. Net charge on the inside is zero. Excess charge resides outside. Net charge on the inside is zero, which means that there's no net electric field on the inside. Electric field is what forces the charges to go through your body. If there's no electric field inside, charges are not going to be forced to go through your body. You're not going to get shocked. All right, that's the Gauss's law. All right, that's the, so now you know the answer. If I have the same question this week, which I will have the same question. The question right now is a little bit more intricate one. I said she can touch the outside of the car. She's still fine. Now you weren't expecting that. The net charge is outside. And net charge, not only is the net charge outside, it's moving. It's an electric current. It's not electrostatics at this point. The charges are moving. There's current. Current is the motion of the charges. I said she could touch the outside of the car. Why would she be fine? Okay, so that becomes the main observation. So this is the last portion of the mystery that we will deal with. How is it that she's able to touch the outside of the car while she's sitting on the inside, obviously, yet she's not getting shocked or electrocuted? That's what we will focus on. All right, so this week's lecture is going to be somewhat...
Bob and I are here to tell you about something that has us very excited.
This week's lecture is going to be after.
NEC's Parabola range of televisions. They've got a 3-year warranty, which we think is fantastic. They come from the same people who have sold over 1 million Australian-made colour televisions. Superb sound comes from the surround sound speaker system, but...
All right, so it's a commercial from Australia. They're trying to sell you high-definition TVs. Quality-wise, out of a 10-point scale, I'm thinking 1. It's a generous 1.
The best feature of NEC's Parabola is its...
And then we jump from 1 to 10.
Lifelike picture.
Because you didn't notice that the person in the background is not a real person. It's just a high-definition TV. And you can't tell the difference. The quality is not good.
Bob and I are here to tell you about something
It's an awesome commercial.
that has us
This guy's going to be as boring as possible. This guy's going to try to look at
very excited. NEC's Parabola range of televisions. They've got a 3-year warranty, which we think is fantastic. They come from the same people who have sold over 1 million Australian-made colour televisions. Superb sound comes from the surround sound speaker system. But the best feature of NEC's Parabola is its
Lifelike picture.
high definition TVs. Believe it or not, guys, 22 years ago, 25 years ago, we didn't have high definition TVs. I came to Chicago in 1996 when I was working on my PhD in nuclear physics in Norfolk, Virginia. And so once I got a handle of the research, I decided that I could probably finish it up on my own. So I decided to move out of Virginia, came to Chicago, got myself a job working at the art school. So they were looking for someone who could teach physics to art students visually. And they asked me to go easy on the math, but make physics as real as possible. And so I thought I was the right person for the job, except, I mean, how do you teach physics to people who are science hostile? And how do you make it visual? It seems pretty easy right now because you guys are looking at the byproduct of what I was able to accomplish. Except this stuff took years to prepare. 25 years ago, we didn't have YouTube, obviously. You can just find videos that you wanted and edit it. Editing technology wasn't quite here. Digital editing was impossible or next to impossible. If you could digitally edit something, it was at most 30 seconds long, no more than that. We couldn't store stuff properly, obviously. We got floppy disk at the time, eventually turned into zip disk. The amount of storage was extremely limited. And then I had to make my own videos. For that, I had to get cable. And then we had VCR tapes. If you don't know what I'm talking about, talk to your parents and I'll explain it to you. So you could record things 6 hours at a time, low quality. Okay. So if this looks low quality to you because it's recording on a VCR.
and I are here to tell you about.
And look at the quality of the image. This is the best that I could do. 6-hour videotapes. And then I didn't have enough time, so I used to record anything and everything I thought might be related to physics. And then you put on a timer, you would record it, and then maybe before going to bed every single night for about an hour, I would just watch something, and then look for something that I could use in physics. And out of a 6-hour videotape, if you're lucky, you'll find something which is 30 seconds long. Okay, because the quality of science programming back then was atrocious. And then next thing you know, I was just looking around for these kind of, if I saw a commercial related to what I was going to talk about, I would just capture it and then edit it and just pull it in. So needless to say, I was spending 60 to 80 hours a week trying to prepare these lectures. And first couple of years, it wasn't going anywhere. I was making like $30,000 a year and spending a lot of time preparing these lectures. And the quality was atrocious. And then that didn't leave a lot of time to work on my dissertation. So immediately 6 months into this experience, I knew that this thing wasn't going anywhere. So I figured that I should just go get a job, research position, 8 to 5, so that I could work on my research at night and just finish out the PhD. That was the whole idea. Lucky for me, there was a company here in Chicago, based in Chicago, and they used to make TV sets, as well as obviously the monitors for computers. The company's name was Zenith. That was a huge company back then. It was almost as big as Microsoft today. And unfortunately, that company, I'm not sure if they're still in business at this point. Anyway, so they were looking for a physicist for research, and I was looking for a physics research job, so I applied for it. They were interested, so I went in for an interview, talking to the HR. So I found out that the salary was, I don't know, $120,000 starting salary, and I'd be working for 40 hours a week. That's like 4 times the money that I was making. So immediately I was interested, no question about it. And so I said, what I need to do, they said, well, just go to the physics department and they'll explain it to you. And then have a discussion. If you're interested, then we'll take it from there. So I just went to the physics department. So I'd walk in, it's a huge room. There's one single desk. There's a guy sitting across a very small table. And obviously there's a chair in front of him. So we introduced each other. And then his first question was weird. He said, how much do you know about the HD TV? Okay, guys, this is, I don't know, this is 1997 or 1998 or something. I said, he said, HD TV. I said, TV, is that television? That's the only question I asked. He said, yeah. I said, what does HD stand for? He said, high definition. I looked at him. I said, what do you mean? He said, it's image quality. He said, so good that it's lifelike, except it might even be better. Okay, I thought he was kidding at first. Lifelike, except it could be better because it said it's going to be digital. Okay. When I was watching the Super Bowl over the weekend, guys, the quality of your TV, obviously the more expensive it is, the better the quality. You can actually see the individual grass on the field. In real life, you would have a hard time seeing that kind of detail because everything is digital. It's lifelike and it may be better. I'm thinking, wow, this is a great idea. All right, so He said that they were working on HD TV, high definition TVs. They had prototypes that they developed 4 years earlier, and they had a slight problem with the prototypes. I said, okay. So he said, do you know how a TV works? I said, yeah, I have a pretty good idea. Because after getting my degree in physics, undergraduate degree in physics, I spent a little bit of time working on my master's in electrical engineering. So I said, you know, if necessary, I can probably build one. They said, no, we don't want you as an engineer. We just need you as a physicist. I said, okay, so what's the problem? So he starts describing the problem. Okay. The problem that he was describing at first sounded really, really simple. Okay, so I'm watching this guy, and he started to draw something out. So let me explain what it is, because this is the setup that we will get to use like a million times. All right, so now this, back then we used to use cathode ray tubes in TVs. Inside a cathode ray tube, you would have a small device which would contain a parallel plate capacitor. Let me tell you what it is. We discussed that before. So one region is going to be positively charged. The other region of it is going to be negatively charged. All right, so this computer is acting up a little bit. Okay, and there's absolutely no reason for it to do that. It's just, everything is lagging. Okay. All right, so I think the RAM is overworked. All right, so you got this region. One plate is negatively charged. The other plate is getting positively charged. Okay, the plate at the bottom, you're looking at a two-dimensional image of it. It's actually a one full plate. There's a hole in the middle. Okay, so the entire plate is getting positively charged. All right, so the negatively charged plate is going to have this filament. You heat it up. What happens when you heat it up? Electrons will become excited. Okay, so what that means in English, you energize the electrons. Okay, so the heat is a form of energy. When you heat them up, they're going to move faster and faster, which means that the atoms, the molecules making up the metal is going to become ionized. Remember the 3 ways you can ionize atoms? Friction is one of them. Heat is the second one. The third one is light. In this case, we're using heat. So this is going to get heated up, and the electrons will become excited. They will become energized, so they will jump out of the atom. All right, so this region is positively charged. This region is negatively charged. All right, so which means that they will be attracted to the positively charged region, and then they will start to accelerate. So the electrons will be given up by the filament. So the filament is going to become ionized. It's going to give up its electrons. And that is going to create this electron beam. And the beam is going to accelerate in this direction towards the hole in the metal. And then it's going to get shot out of the hole. All right, so this setup is going to shoot electrons out of it. So that's the reason why the engineers call this an electron gun, because the engineers are cowboys. And us physicists, we call it a capacitor. Okay, so it's just going to shoot out a stream of electrons, and then you have an electromagnet within this region. So what the electromagnet does is just going to stream the electron beam onto the screen a couple hundred times per second if it's a regular TV, a few thousand times per second if it's high definition. All right, so that's the basic setup. All right, so how do you go from a basic normal regular TV to high definition? What you need to do is you need to increase the strength of the electric field. And that's all you have to do. Make the electric field extremely strong within this gap, the opening. As a result, what's going to happen is the electric field is going to induce a much stronger force on the charges. As a result, the charges will accelerate at a higher rate, which means that the charges, upon being shot out of this hole, will be moving much faster. As a result, you can take the charges and stream it across the screen a few thousand times per second. Okay, so the problem of doing it this way, they noticed, is when they created extremely strong electric field, while it is definitely generating a faster moving charges, it would also generate a spark within the gap, and then the spark would zap the electrons. That's it. All right, so that was the problem. All right, so he told me that each and every single prototype was costing them $10,000, and they had an average lifespan of 6 months. Okay, every single one of them within that six-month time period would develop an internal zap, and that would fry the electronics. Okay, so he said, what do you want me to do about it? He said, fix it. Okay, the nice thing about this is I kind of had an idea, all right, which is very unusual because it's in research, whenever you start working on something, it's very rare that you walk into some kind of a research field and you know immediately what's going on, and then you already have a few solutions in mind, a couple of things that you want to try. Real life doesn't work out that way. Only in the movies you see that kind of stuff. In real life, you get into your research field, at least for 6 months to a year, you have no idea what's going on. You're completely confused. It takes you about a year to get a handle of what's going on. And then you start generating some ideas, and most of your ideas are either not sophisticated enough or no good. It takes a few years before you start to develop some good ideas. You have to read research papers, check to see what's done in the field, check to see why they have done it the way they've done it, and how well it worked out. Okay, in essence, today during the lab, that's the sort of stuff that you will do, because I'm giving you 2 mysteries, and then you will investigate it, and only to realize that, hey, there are people, smart people thinking about it, and they're trying to solve the problem, but evidently we don't know the answers yet. So I want you to see the process. This stuff is not easy. Okay, this happens to be a weird situation. I walk in, I see what the problem is, and I think I have an answer for it. In fact, this is one of those weirdest things. And not only did I understand what this guy was talking about, also I thought that I knew the answer. Okay, so I was about to volunteer and make a few suggestions, only to realize that I didn't have the job. So I figured that I should just shut up and let the guy talk and ask questions. I said, great. I said, so you said you guys were working on it for 4 years. I said, how many people were working on it? Because I'm thinking this is a big company, so they probably have 10, 15 physicists working on something like that. They said, me and the other guy. I said, how many people were working in physics? He said, me and the other guy, only 2 people. I said, what's your background? And he said, engineer. He had a minor in physics. Okay, so at that point, I kind of figured, I knew that he was an engineer because the way he was describing this, he was using engineering terminology. We don't call it an electron gun, right? That's an engineering thing. And then also, I make the assumption that the reason why they weren't able to solve the problem because these guys are engineers. Okay, it's a physics problem at first. And engineering is applied physics. Engineers usually don't understand physics to the same level, okay, because what they do is a little bit more hands-on. I said, how about the other guy? He said, oh, the other guy was the research leader. He was a physicist. He had a master's degree in physics. I said, okay, so the other guy was doing the research and this guy was helping him out. Okay, so I said, great. So what are the things you guys have done over the past 4 years? Evidently, the other guy quit. That's the reason why the position is available. He said, he mentioned a couple of things. The first couple of things that they had done was identical to what I was thinking, all right? In fact, those are the stuff that I was thinking. They tried that from the get-go. Like they spent about a week, 2 weeks or whatever, and then they took that approach, initial approach. It didn't work, all right? It didn't work, okay? So what I was thinking didn't work. That was intuitively, that's the direction that they decided to approach it. And then they came up with these methods. They were really sophisticated the first year. None of the stuff that they tried worked. And it was really impressive. And the second year stuff was unbelievably impressive. I was just sitting and drooling. It was that good. They tried this and that, and it was just explaining the details. I'm just sitting and enjoying it. And I'm just keeping up with what he's saying. And then nothing is working, nothing. And then they exhausted anything and everything that you could do using physics. And that's it. So that's the first 2 years. I said, great. So the third year, I'm thinking they came up with something even more fascinating and exciting than what they came up with during the second year. No, all of a sudden, there's a sharp left turn. They started applying these advanced statistical methods to this problem. I kind of remember just sitting there rolling my eyes, and then he didn't notice it, thank God, because you shouldn't be doing that during an interview. Because the advanced statistical methods are not applying it, right? That's the sort of stuff that I used to do at Fermilab. This has nothing to do with this sort of problem. So I couldn't quite understand why they were doing it, but they were doing it. I said, who came up with that? He said, the physicist did. I said, what for? He said, well, he had a bit of a justification because nothing was working. He wanted to know if we could actually approach it from advanced statistical methods or what. I said, okay, so what happened? It didn't work. The third year, they came up with these advanced statistical methods. The fourth year, they came up with even more advanced statistical methods. Nothing worked. And then the other guy quit because he became so good at statistics, he decided to get a PhD. I'm thinking, oh, I see what the guy did. What the guy did, in essence, is clever. First 2 years, they tried physics. It wasn't working. They tried everything under the sun related to physics. Nothing worked related to physics. At that point, I knew that this wasn't a physics problem. I had a rough idea of how you could solve the problem, but that requires material science. It's not physics. This guy had a job. All right. He knew that he could just, they give you only so much time to solve this problem. If it's not solved, they're not going to invest in it. So he knew he was probably going to lose the job at some point. So he decided to make it look like it was something that could be solved using statistics. Obviously, he was interested in it. He was getting paid $125,000 a year. So why not make $250,000 and, you know, get better at your craft and go get a PhD. So I think that's what this guy did. And all of a sudden the job becomes available. So this guy thinks that I'm going to be able to solve this problem. At this point, I'm sitting there evaluating it. Is it really worth my time? Because I don't think that physics is not going to work. I can fake it like the other guy, make some money, but eventually they will pull the research money out of it because I won't be able to solve it. So I'm listening to the guy. I said, at some point I got to a point, I decided that, nope, it's not really worth my time or the effort. It's just too risky at this point. I said, what else do you guys have? He looks at me because I seem disinterested at this point. He said, oh, we'll find you something else after you're done with this problem. I'm thinking we won't be able to solve this problem because I don't see physics in it. And material science was a thing which was coming up at the time. It's a big thing. And material science is an extension of solid state physics and chemistry. And my thinking was that just come up with metals that's going to be able to hold on to their charges at extremely high, strong electric fields or high voltage fields. Okay, it seems like it's pulling electrons from the surface, which is not supposed to, but it is. I don't know what's causing that to happen. That's still a mystery today. And somehow the positive charges, it's just pulling charges from this plate. Somehow it's not, like I said, I can't, even today, I cannot understand how that's happening, but that's what's happening. Okay, it's just that. So you need to have something that's going to be able to hold on to its charges at extremely high voltage fields. And that's something that could be engineered, as far as I was concerned, using material science, but I'm not going to share that knowledge, obviously, because I may still be interested in the job. So I said, what else do you have? He said, said, we'll find you something else. I said, would you be interested in a problem like this? I said, I have to think about it. As soon as I said that, he's like, you know, you can publish this in high voltage magazines. He said, I know you're a nuclear physicist. This is beneath you, but this is something that you can actually publish. I said, I understand that, but I have to think about it. As soon as I said that, it's like it's reversal of roles. All of a sudden, there's a bit of a desperation in this guy. He said, is this because of the money? We can pay you more. I'm thinking, yeah, I don't think that's going to really solve the problem. So I thought about it. I said, from my perspective, I don't see a solution because they tried anything and everything. I thought about it for a few days. I called up the human resources. I declined. I explained the situation. I said, you guys may be better off getting someone who's an expert in material science, because I knew people who were getting PhDs in that field. I had a rough idea of what needed to be done. Not concise, because it's not my field. Anyway, so I get a call back about a week later, and they say, hey, they shut down the physics department, so that poor guy ended up losing his job. They moved everything to Korea. And then that's it. Okay, so that kind of makes sense because, guys, it's 4 years research. They had something which was working, needed a little bit of fixing. They poured a lot of money in it, and no results. Basically, they wasted 4 years. So why not just move everything to Korea? I mean, Korean physicists, engineers, material scientists, they're probably just as good. Most people, on average, more or less the same thing, except it's cheaper. And then I don't quite know what happened in Korea. They were not able to come up with a high-definition TV, at least not on time. All right, so they end up losing their market dominance. Obviously, they had to close down their factory in Chicago, and they entered into the market way too late. They came up with a digital TV, and then they came up with their high-definition TVs. It was way too late. I don't know what happened, so they lost their dominance. And so I went back to our school, and then you guys are looking into byproduct. Okay, so my question is the confusion that I had. I still do have that confusion. The question is, what the hell is causing this to happen? Okay, so a couple of things. It's because it's exactly the same question that we have regarding lightning. There's always a mystery, and the mystery here is even bigger. Okay, I mean, he was talking about high voltage fields. You can actually publish this in high voltage magazines. What is voltage? All right, so that's one of the discussions that we will have. The second thing is, what caused this spark to happen? This is like, it's one of those, to this day, I think about it. This is so weird. To this day, it's almost 25 years. I'm like, what happened there? Forget about how you fix it. What's causing this to happen? And it's the sort of stuff that keeps you up at night when it comes to lightning. And lightning is something that we understand slightly better. All right, so the electric potential energy. Ooh, okay, so this is going to require a really fast review. Okay, so we'll do a fast review regarding energy. Energy is an abstract concept. Abstract doesn't mean it's complicated, it's just a step removed from life. Okay. These guys not only use the concept of energy, they kind of abuse this. So those of you guys who are taking physics 1 with me will remember that.
To plan as they leapt off the bridge while tethered to the cable.
Stand up. On three, going. On three, double. On three. 1, 2, 3, go.
But as the team was about to reach the end of their first arc, the cable snapped. And 4 men and 1 woman plummeted 70 feet at 80 miles per hour, slamming into the water with terrifying force.
Okay, I'm on the outside helmet cam. Kenny, myself, boy, Sarge. She does the front flip. Here we come, going into full velocity right here. Probably reached about 78 miles an hour, right about here, 78 miles an hour. You'll see the harness disconnect from the cable right there. Didn't the seat just disconnect? My arm goes out, and here we come to the water. Kapow! Oh, a ton of bricks. So look at the splash, like 40 feet. We could action though.
All right, so a couple of
according to plan.
Couple of questions, if I could just with the computer. All right, so they knew that we're going to be going at 78 miles per hour right at that point. So the question is, how do they know? They'll hit the water at 91 miles per hour. So the question is, how do I know? And the third question is, if they were to jump directly into water as opposed to doing the pendulum move, would they be hitting the water at a speed larger than 91 miles per hour, slower, or the same? Okay, so those of you home with me should remember the answer. All right, so let's do a fast review and then answer those questions. Okay, so energy means the capacity to do work. So that's the basic definition. Okay, so whatever energy is, if you have it, it should give you the ability to do work. So the question is, what is work? What is something that happens when there's a force causing displacement? All right, so there's a force causing displacement. So there's force acting on this. And as a result of the force, this car is moving along the direction of the force in this case. So whenever you do work, it's a process of transferring energies. So by the amount of work that you do is you transfer energy. That's the amount of energy you get. So the proper unit is going to be joules. In the United States, we use calories. The United States calorie is the same as a kilocalorie. So you see the conversion factor. Okay. All right, so this is known as the work energy theorem. Force causing displacement. So force is acting on it, gets displaced. All right, so in every single reference book or textbook, it's F times R or S, it doesn't matter. All right, so R could be X, Y, or Z, or something in between. So force causing displacement is known as work. So what happens when there's work? Energy gets transferred. All right, so kilocalories in the United States, calories, so we got the conversions. Okay, so what else do we need from here? All right, so I think that's it. All right, so the amount of work that you do is the same as the amount of energy that you transfer. Okay, so work is a process of transferring energy. Delta E represents the change in energy. All right, so delta means change. Or D if you're using calculus. All right, force on the crate, no displacement, no work is being done. Applied force acting on it is getting displaced, so work is being done, the energy is being transferred. So speaking of work, force has to be responsible for the motion itself, the displacement. So if the force is coming at an angle, it needs to have a component on the direction of motion. That's the main. Once again, there's force coming at an angle, the force has to have a component on the direction of motion for it to happen. All right, a couple of things that we need to emphasize. If the force is coming at an angle, we are going to be interested in the component of the force that's going to be responsible for that motion. This is the component of the force which is parallel to displacement. That's what it means. So it's going to be the cosine of the angle of the force times the displacement is the amount of energy that you transfer. All right, so the background is obvious. Positive times positive is going to be positive, blah, blah, blah. All right, if you don't know what I'm talking about, just go back to your grammar school notes. All right, so direction matters because we're dealing with vectors. To the right, positive, to the left, negative. Up, positive, down is going to be negative. Forces, likewise, to the right, positive, to the left, negative. Up, positive, down, negative. All right, so we will do vector multiplications as it so happens. So 3 cases, the mass is getting displaced horizontally. In the first case, the force causing displacement in the same direction. Second case, opposite direction. The third case, it's going to be 90 degrees. They're perpendicular to it. Force and displacement in the same direction, positive work. Force and displacement are in opposite directions, so it's going to be negative work. Force is 90 degrees to motion, which means that the no work is going to be done. Positive work means that the energy is gained, so the energy is increasing. Negative work means that the energy is being lost, so which means that it's losing energy. And no work means that the no energy is being transferred. Okay, so that's what it means. All right, lifting something up, the work is positive, force and displacement are in the same direction, energy is gained. Carrying something forward, constant speed, straight line, no change in speed, no change in direction. All right, so force is 90 degrees to motion, so this force does not contribute to motion, no work is being done, no energy is being transferred. If that's the case, putting something back down on the ground, force is in the upper direction, the displacement is in the downward direction, force and displacement are in opposite directions. All right, so the work is negative, the energy is being lost. Force of gravity extending all the way out to the moon. How much work is being done by the moon, by the Earth on the moon? How much energy is being transferred to the moon by the force of gravity? The answer to that question is none. Why not? Because the force is 90 degrees to motion itself, so which means that more work is being done as a result. All right, guys, just give me a minute. All right, so just watch this. I need to change the mouse. Okay, so let's check to see how well this works. Okay. And let's get rid of one of them. All right. All right, this one is obeying my commands. All right, so this formula represents the reality that we just set up with. One force and displacement are in the same direction, angle is going to be 0, cosine of the 0 is going to be 1. Okay, so work is going to be positive, so the energy is going to be gained. Force and displacement are in opposite directions, so this is the case that you're looking at. The angle is going to be 180 degrees. Cosine of 180 is going to be negative 1. So it's going to give you negative work, which means that the energy is lost. The third case, the force is 90 degrees to displacement, so cosine of 90 is going to be 0, so work done is going to be 0, so no energy is gained. Okay, that's it. Okay, so the formula is work. Okay, so work is a process of transferring energy. Cool, we got that. So what that means is by the amount of work that you do, you end up transferring energy to the object. So you're lifting something up, work is done against gravity, you apply a force on something, and then that gets displaced in the direction of the force. So positive work is being done. So the object that you're lifting is going to gain energy. So which means that by lifting something up, you energize that something. Object gets energized. All right, so the amount of energy that you transfer to the object becomes stored in that object. So that stored energy is known as potential energy. Okay. these are kind of book definitions, so we have to kind of clarify this sort of stuff. All right, there's more to it than that. So that more to it than that stuff is the stuff that I'm going to emphasize. So lifting something up, you're doing work against gravity. All right, so this got weight, so you're lifting it up against gravity. So you're doing work on it in essence. So the amount of work that you do by lifting something up is the amount of energy that you transfer. So the energy that you transfer is going to go to the potential energy of that mass. Okay, so a couple of things to look at it. Potential energy is the stored energy. It depends on the height. You store energy by doing work on the object. That's not good enough, because that's, if I describe it like that, that's an incomplete statement. I'm doing work on this object by lifting it up. I'm doing work against gravity by lifting it up, because gravity is going to keep pulling it in the downward direction. In essence, what I'm doing is I'm taking the weight of this object, which is mg, and I'm just displacing it against gravity. All right, so mass times gravitational acceleration is going to give you the weight of it. So the weight of this mass is displaced in the upward direction. So the work done against gravity will become stored in that object. So that's potential energy. Potential energy only depends on the height, the location inside a conservative force field. Whatever that is, the meaning of the conservative force field is something we will discuss shortly. All right, let's get out of here. So gravitational potential energy is the stored energy. So that's the energy that an object has by virtue of its position above the surface of the Earth. Okay, that's an incomplete statement, but position matters, the location matters when it comes to that. Second type of energy that we'll be interested in is the kinetic energy, energy of motion. This is the kinetic energy. All right, so kinetic energy is the energy of motion. Notice that this is speeding up. Going from 20 meters per second to 30 meters per second. It's speeding up, meaning that it's accelerating. Because acceleration is a force, which means that there's a force acting on it in the direction of motion. That implies positive work, which means that the energy is being transferred to the system, and the energy transferred to the system is going to appear in the form of speed. It's going to appear in the form of motion, so hence the reason why this is known as kinetic energy or the energy of motion. And that's the meaning of it. So here's your kinetic energy, that's the energy of motion, and it's going to be related to speed, square of the speed times mass divided by 2. It's going to give you the energy of motion. So kinetic energy depends on the speed. The faster you go, the larger the kinetic energy is. Combination of kinetic and potential energies is known as mechanical energy. If the mechanical energy is constant, it's said to be conserved. Conservation of mechanical energy is the constancy of mechanical energy. So if mechanical energy is conserved, what that means is that kinetic energy can turn into potential energy, and potential energy can get converted into kinetic energy. Drop a ball, potential energy goes down, kinetic energy goes up, which means that the falling ball is going to speed up. That's what it means. All right, so the next, and that statement is correct, provided that mechanical energy is constant, conserved, provided that it's constantly conserved. So the next question is, what conserves mechanical energy? So mechanical energy is going to be conserved by any force that conserves mechanical energy. Damn, that's a one circular argument. Any force that conserves mechanical energy is known as a conservative force. Okay, so when you drop a ball, potential energy goes down, kinetic energy goes up. Potential energy gets converted to kinetic energy because the mechanical energy is constant. Why does the ball fall? Because of gravity. Okay, so gravity is an example of a conservative force. So mechanical energy remains the same. If gravity is the only force acting on it, what happens? It converts potential energy into kinetic energy. So example of a conservative force is gravity. The second example that we saw in physics 1 was the restoring force. So gravity and restoring force are the conservative forces. It's a process of transferring energy, but work is something that happens when there's force causing displacement. Force influencing displacement is probably a better way of saying it. All right, so it's a combination of force and displacement. Force could be in the same direction as displacement, so which means that it's causing the displacement, or it could be opposing the displacement, so it depends. Positive work is when the force and displacement are in the same direction. Force and motion are in the same direction. All right, let me check to see if this is working. All right, so force and displacement are in the same direction, work is positive. Force opposing displacement, work is negative. Force having no component with this along the direction of motion, no work is being done. All right, so the work could be positive, negative, or no work. Positive work means the energy is going to be gained. All right, come on, let's go. All right, so when the work is positive, energy is gained, negative energy is lost, and blah, blah, blah. All right. Okay, so what's positive work, negative work, and no work? Okay, so work is going to be positive when force and displacement are in the same direction, obviously. Negative when they're in opposite directions. And we've seen examples of it. I don't want to spend a lot of time on it. Okay, so what else do I want to emphasize? All right, when it's positive, the energy is gained. When the work is negative, the energy is lost. No work, transference of energy. I think that's as far as I want to go with that. Okay, so. All right, so how much work does gravity, force of gravity, gravitational force perform on the moon? All right, so gravity extends all the way out to the moon, right? So how much work is being done on the moon by the force of gravity? How much energy gets transferred to the moon by the force of gravity? So the answer is going to be none, because the motion is along the direction of velocity, right? And the force is 90 degrees to it, so no work is being done. All right, so no energy gets transferred in essence. Okay, so what else? We talked about potential energy, so that's the stored energy. Depends on position. We'll take a look at it a little bit more closely and formally. The potential energy is the amount of energy that you store or transfer to an object by the amount of work that you do against gravity. Why is that statement important? You'll find out shortly. All right, kinetic energy is the energy of motion related to speed. Mechanical energy is a combination of kinetic and potential energies. The meaning of conservation of mechanical energy means it's constant. Okay, so when you drop a ball, what happens is kinetic energy is going to go up because the ball is speeding up. Potential energy goes down because the height is decreasing. And mechanical energy is not going to change. All right, that's good enough. All right, that was the review. All right, so if gravity is the only force acting, potential energy is going to turn to kinetic energy. That's it. Remains constant. Potential energy turns.
Stand up.
The group is ready.
Okay, so,
Ready for the jump.
78 miles per hour right there. How do we know that? Well, we know that obviously because somebody did the computations for them. They knew it was 78 miles per hour because they end up using the conservation of mechanical energy. All right, so this is the length of the cable, 200 feet. I usually measure the distances with respect to the lowest point of motion. So the lowest point of motion is going to be zero height. Initial height is going to be the length of the cable. All right, so what else do we have? All right, so gravity is the only force acting, mechanical energy is conserved. Final height is zero, the initial speed is zero. Boom, 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 you got the algebra. And then eventually you come up with this answer, according to which the final speed only depends on the initial height. Anyway, so plug the numbers in. G roughly about 10. And it gives you a number in terms of metric units, and then it's about 78 miles per hour. So that's how it is now. So conservation of mechanical energy is a really useful mathematical tool that we will keep employing time and time again. All right, and that's one of the things we're going to do today, honestly. All right, just again, there we go. All right, so the next question is.
The other is
All right, just 78 miles per hour right there. 91 miles per hour right there. All right, how do I know that it's 91 miles per hour? It's the same thing. So gravity is the only force, I think. All right, so this time the final height is going to be the water level. Initial height is the length of the cable. That's 200 feet. And then after the cable snap, there's an additional 70 feet drop. So the total distance is going to be 270. All right, so gravity is the only force acting, so we ignore air friction. So what's the final speed? All right, so do the conversion. And once again, it's the mechanical energy is constant. So here's your initial, here's your final mechanical energy. And then I'm just going to cheat, just grab the same solution. So the final speed is going to depend on the initial height only. Plug the numbers in. It's about 91 miles per hour. About 91. Okay. What if these people decide to jump? All right, so if we forget this, they go, okay, well, forget it. Let's hold hand, suicide pact, just jump. What do you think is going to happen? Do you think the speed is going to be larger, the same, or smaller? Well, once again, assume that mechanical energy is constant, so ignore friction. And final height is going to be the same. It's going to be zero. Initial height is going to be the same. All right, so in essence, you're forced to use the same equation. And then when you're done with it, what happens? You will come up with the same answer. All right, so you will get to use the same equation. So which means that final speed is only going to depend on the initial height. So what that means is if this is 91 miles per hour, this one is also going to be 91 miles per hour. Except this takes shorter. This is going to take a little bit longer. If you want to do sightseeing, this is the way to go. And if you're in a hurry, this is the way to go. So what did we learn from this? Path of motion does not matter if there's a conservative force acting. If the motion is under the influence of a conservative force like gravity, path of motion doesn't matter. What matters is the initial and the final points of motion. That's it. So path of motion is not going to matter if you're dealing with conservative forces. If there's a conservative force acting, what happens? The mechanical energy is conserved. So if the mechanical energy is conserved, the path of motion is not going to matter. If I were to ask you which ball is going to be moving the fastest, hopefully you would know the answer right now. In all three cases, the ball is going to be projected from the same height, so it's going to have, all three will have the same potential energy. All of them are projected at the same initial speed. So what that means is all of them have the same initial kinetic energy. So their initial mechanical energies are identical in all three cases. All three have the same mechanical energy. The ball leaves your hand, gravity takes over. So what does gravity do? It's going to convert that potential energy into kinetic at the moment of impact. So which means that all of them are going to move in. Okay, so we're still having a problem. Okay, cool, that's fine, we'll fix it. So we're down. It's acts like a particle accelerator, believe it or not, a simple particle accelerator. This is known as an electron gun if you are a engineer. All right, so here's how it goes. You got two parallel plates, one negative charge, the other positive charge, and you have a metal filament right there. So the filament is going to get heated up, so it becomes ionized, which means that it's going to give up its electrons. It generates an electron beam, and then obviously the electron beam is going to accelerate towards this hole. Dimensionally, it looks like they're not connected. Three-dimensionally, there's just a hole in the middle. It's not a gap, it's just a hole. So these electrons are going to be shot out of that hole, and because this little device ends up shooting electrons, engineers call it an electron gun. It's a capacitor. And then by using an electromagnet, you can just trace the electrons onto a screen. And next thing you know, you got your TV, obviously. That's the idea. So the whole idea is to get the electrons to accelerate in this direction at a constant rate so that the motion is predictable, right? So for you to be able to do that, the strength of the electric field has to be constant. Electric field is going to induce a constant force on the charges, so the charges will have a constant acceleration. And that gives you a predictable motion. All right, it just so happens if you make the electric field extremely strong, all right, so that's the reason why the guy was saying high voltage. And he was talking about high voltage research. Whatever voltage is, that's the discussion of this week's lecture, obviously. Next thing you know, you end up generating this accidental zap, which is Friday electrons. All right, so what's causing this zap? It's the same question that we had regarding lightning. Okay, not everything is well understood. And this thing is just, I'm still baffled. I still have no idea. I had a bit of a theory on it, but I was not able to convince myself as to what was generating within that setup. And obviously the Zenith was not able to solve that problem immediately, so it took them a while. Other companies solved that problem, but today's technology is completely different. So I don't think they're using cathode ray tubes today. I don't know what they're using. All right, so, all right, let's talk about potential energy. So potential energy is the stored energy, right? So how do you store energy in anything? Well, for you to be able to store energy, what you need to do is you have to do work against a conservative force, like gravity. All right, so by lifting up, you're doing work against the conservative force. The amount of work that you do against the conservative force is the amount of energy that you end up storing in that object. All right, so along the same lines, here's a positive charge. Here's another positive charge. She's going to bring this positive charge near the other positive charge. All right, so you know that there's a tremendous amount of repulsive force acting, right? This force is being repelled by this one. So you have to do work against that repulsive force, electrostatic force, to bring it near. So by bringing this positive charge near another positive charge, you have to do a tremendous amount of work. So the amount of work that you do is going to go into the potential energy of this charge. All right, so it becomes stored in that charge. So what happens when you release this charge? You bring it near this one and release it. All that potential energy will turn into kinetic energy. The reason why it's going to turn into kinetic energy is because electrostatic force is also a conservative force. So the electrostatic force acting on this charge is going to convert this potential energy into kinetic energy. That's it. Which means that the mechanical energy is going to be constant within this region. There's another illustration of it. We got a parallel plate capacitor. One region is positive charge, the other negative charge. All right, so we'll bring positive charge near the positive charge region. So we have to do work because there's a tremendous amount of repulsive force acting on this one. So by bringing it near, we energize it. So now it's got potential energy. Now this got potential energy. So what happens when you release it? That potential energy is going to turn into kinetic. As the potential energy goes down in this direction, it's going to turn into kinetic, which means that it's going to speed up. And the path of motion doesn't matter. It doesn't matter that you bring the charge from here to there by taking the shortest path or the longest path. It doesn't matter. The only thing that matters when it comes to transferring energy is the endpoints of motion, initial and final. All right, so what happens if I let the charge go and now it's got potential energy, right? So when you let it go, that potential energy will get converted into kinetic energy. So the conservative force acting on the charge will reduce its potential energy and then it's going to turn it into. That's what the statement is saying. Okay, once again, this is borrowed from physics 1. Work done by a conservative force, that has to be a C here. There's a negative sign. It's going to act to reduce the potential energy of that mass or of that charge. So the work done by a conservative force reduces the potential energy. And then while it's reducing it, it turns into kinetic energy in essence. All right, so far we talked about potential energy. Initially, we talked about the gravitational potential energy. Now we're dealing with the electric potential energy. And topic of the lecture is potential. So what is the relationship between potential energy and potential? So I'm about to emphasize that. So number one, here's a little bit of a warning for you guys. This concept is abstract. It's extremely abstract. If you don't get it right away, that's normal. All right, you have to kind of think about it. Eventually, it sinks in. Except there's no way of getting around it. All right? Potential, a concept of voltage and potential, is going to remain with us forever. Okay, because everything that we will do from now on is going to depend on what we are covering. I want you to get a really good understanding of it, because if you don't get this stuff, you're going to try to do your physics and engineering mathematically, though it can be done, There's no question about it. You can try to fake it, and you'll probably get away with it up to a certain point. The experience of it is going to be excruciatingly painful because this is a simple enough concept. It's abstract. Means it takes a little bit of work to get at it, but once you get a good grasp of it, this is a powerful concept. But if you try to do it blindly and mathematically, I got to tell you, it's going to be one of the most painful experiences to do physics or engineering. Right? Just understand the concept. Once it sinks in, it's easy to use, easy to apply, and then also all of a sudden you have a really good understanding of what's going on. You can actually visualize what's going on when it comes to these electrical systems. Right? We don't have that kind of luxury in modern physics. There's nothing that we can visualize. The classical physics is, if you can visualize it, it's like a Disney show in your head. I mean, this stuff is so easy to grasp once you make the connections. All right, so now you guys understand the meaning of potential energy. So that's the amount of energy stored. So how do you energize something? Well, you know what? You have to do work against a conservative force field. Like gravity, lift something up. What are you doing? You transfer energy, it becomes stored in the object that you're lifting. How do you energize a charge? If it's a negative charge, bring near a negative charge region. So you're doing work against the electrostatic repulsion. The electrostatic force is also a conservative force. Or bring a positive charge near a positive charge region. So you're just energizing. Now, potential is actually an easier concept than potential energy, but it's got like 2-3 different ways of interpretation. So I want you to know all 3 interpretations or 4 interpretations or whatever. They all mean the same thing, except you're looking at a reality from different perspectives. All right, so positive charge region is known as the high potential, and negative charge region is known as the low potential. All right, so if the region is positive charge, we call it the high potential region. If it's negative charge, we call it the low potential region. We're always interested in the potential difference. That's it. All right, so high potential versus low potential. High is almost like a higher elevation. Low is like a lower elevation. So you're almost dealing with like height difference in essence. The other thing that I want you to notice is the electric field always points from a high potential region towards the low potential region. All right, so positive charge region, high voltage, high potential. Voltage and potential, they mean the same thing. And the negative charge region is going to be low voltage or low potential. Okay, if you're not understanding the significance of it right now, don't worry about it. There's no significance right now. I'm just labeling stuff. Because we always talk about potential difference. The potential difference is the difference between high potential and low potential. For voltage difference, it means the same thing. One region is going to have high voltage, the positive charge region. The other region is going to have low voltage, it's negative charge region. Okay. This has high potential energy and low potential, but that's an argument for another time. So I don't want to worry about it. Okay, another thing that we need to focus when it comes to capacitors, because that's what I'm putting the emphasis on right now. Electric field within this region is going to be constant. Okay, we dealt with this last week while we were dealing with the Gauss's law. Okay, the reason is because number one, net charge is composed of like charges. And obviously you put the net charge on a metal surface of metal or on metal, let's say on metal is good. So like charges will get repelled. All right, so they will get repelled to the surface. And then once they're at the surface, so they're going to keep moving until the net force acting on each and every one of them is 0 in the along the direction of the surface. So all of them are going to be equidistances from each other. And obviously there's not going to be the electric field component parallel to the surface. The only surviving component is going to be the vertical component. So all these electric field lines will be equidistant from each other and they will be constant. They will be parallel and constant. Okay, that was too much explanation. All right, so back out of it. So what's happening is, so the charges will be uniformly distributed onto the surface area. So charge density is going to be constant. The electric field strength is going to be constant within this field. So constant electric field acting on the charge is going to cause a constant force. So the constant force acting on the charge is going to use constant acceleration. When the acceleration is constant, motion is predictable. So which means that each and every single charge upon leaving this opening, the hole in the metal is going to be leaving at the same speed. So which means that by using an external magnetic field, you can actually trace the charge onto your screen. So if you're televising an event, what you're capturing elsewhere is exactly what you're seeing on the TV screen, but that makes motion predictable. All right, let me just back out of this one more time. If it lets me. All right, so another way you're looking at it. Okay, so I looked at it from a kinematics perspective. Now I'm going to look at it from a conservation of mechanical energy perspective. All right, the way you look at it, so this region is negatively charged. I put a negative charge there, so which means that the charge is energized, so it's got potential energy, right? So what happens when there's a conservative force field acting on it? That potential energy turns into kinetic energy at that point. So potential energy is going to go down while kinetic energy goes up. So potential energy gets converted into kinetic energy. All the charges here will have the same potential energy, and all of them will have the same kinetic energy upon exiting this hole. Once again, it's the same statement as the constant force is going to give uniform acceleration is going to make motion predictable. All right, so the question is, we know what potential energy is. So this is the amount of energy stored. We talked about potential in terms of potential difference. Positively charged region is going to have high voltage or potential. The negatively charged region is going to have low voltage or potential. This represents a potential difference in essence. All right, so what is the meaning of this equation, the right-hand side of it? All right, so now the next portion of the lecture is going to deal with this. How do we tie potential energy with potential? Okay, so this is a nice little description, and it goes like this. Okay, so high voltage, low voltage, high potential, low potential. So that's one definition. Now this one is going to be a deeper definition. This is the one that I'm interested in. All right, so here's a capacitor. One region is positively charged, the other region is negatively charged. So the electric field is pointing in the downward direction from positive towards the negative charged region. R is going to represent the separation distance between these two regions. Notice that the product of the electric field and separation distance is going to give you the voltage or potential difference. All right, and this is exactly the reason why I don't have a textbook, because this is a textbook definition of it. If you got nothing to say, this is how you talk usually. So what does it mean? I just described the formula for you, but what does it represent? I didn't say anything about that. So that's what we need to talk about. So what this represents, literally, this represents the amount of energy stored within this electric field between these two opposite charged regions, which are separated through a distance of r. That's what it represents. Okay, so there's a deeper meaning, which is tough to capture by the textbooks. So what this represents is literally this says, hey, this is the amount of energy stored within this electric field between these two opposite charged regions separated by this distance. Just remember. So when you're dealing with potential difference, what that means is one region is literally positive charge, the other region is negative charge. The term, just when you see this term, when you see a potential difference in terms of charges, immediately that should conjure up the image that, hey, you're dealing with a region in between two opposite charges. All right, so one region is getting positive charge, the other region is getting negative charge. All right, and what does this represent? It represents the amount of energy stored within this region, but the amount of energy is going to be stored within the electric field, and the amount of energy is going to be stored within the electric field between two opposite charge regions, which are separated through a distance of r or d or whatever. Okay, so understand, because these formulas are literally summary statements. This is not math, guys. We use mathematics to summarize ideas. All right, so now all of a sudden I go, initially you went, oh, the potential means, oh, positively charged region is high potential, negatively charged region, low potential. It's not abstract, so it's, instead of saying, oh, this is positive charge, you say high voltage. Instead of saying this is negative charge, you're saying low voltage. But all of a sudden this voltage starts to take meaning. It means that when you have a region, you have two opposite charged regions, energy is going to be stored in between, and how much energy is stored in between is actually indicated by this voltage or potential difference. And the energy is going to be stored literally within this field. This is the electric field, electrostatic force field. All right, we're not done yet. Okay, now the terminology. Okay, voltage and potential, they mean the same thing. I've mentioned that before. I'm going to keep mentioning it until your brain stops fighting me on this. All right, when we say voltage or potential, we mean voltage or potential difference. Voltage and potential difference, or potential difference, they mean the same thing. So delta V means voltage difference, delta V means potential difference. And sometimes we get lazy. Michael becomes Mike, for example, right? We do the same thing here. Robert becomes Bob, all right? Potential difference becomes potential. Voltage difference becomes voltage. It's the same thing, all right? It's just the laziness in expression. So instead of looking at delta V, now you're looking at V, which is the voltage or potential. So that's going to represent the amount of energy stored within this electric field between two opposite charge regions, which are separated through a distance of r. All right, so voltage or voltage difference is the same as potential difference. It's going to be expressed in terms of volts, named after Volta, is an Italian physicist. So we got the electric field, newtons per coulomb. R is going to be the separation distance between two opposite charge regions. All right, now I think we have a better idea of what voltage or potential is. All right, so this yellow region that you're looking at is where the energy is stored. The energy is stored within the electric field through a separation distance between the two opposite charge regions, separation distance of r. All right, let's add on. Okay, so what else? Stronger the electric field is, more energy is going to be stored in that region. All right, now this is going to start to make a little bit more sense. So far, I'm just swimming in abstraction, and you guys are not quite grasping the importance of it. And then hopefully you will go, okay, now it starts to make sense. Now, what would happen if I were to place a charge here? Okay, guys, this region is energized. So what happens if I were to place a charge there? What happens is this charge now becomes energized, right? So this region was energized when there was no charge. As soon as you place a charge in it, so what happens? Charge becomes energized. By virtue of placing the charge into this field, I energize the charge. So what happened now? This charge is potential energy. All right. Okay, so couple of things. I'm modifying some terminology. So I would use PE. I think that's what I did in physics 1. Now PE, potential energy, becomes U, capital U, to denote, once again, potential energy. It depends on the book. If I'm teaching a lower level physics, I like PE better because students understand it better. At this level, you guys are taking university physics, so commonly we use U. Some books use V for that, okay? And this V in higher level courses becomes phi or phi. Okay, so these notations keep changing. So U is the same as potential energy. That's the only thing you need to remember. All right, so how did I energize the charge? I energized the field. All right, so which means that I created a potential difference, meaning that this field was energized and the energy was stored in the electric field. So which means that I created an electric field region. All right, so the field was energized. So I placed the charge in it. As soon as you place the charge in it, the charge becomes energized, which means that the charge right now has potential energy. That's it. All right, so potential turned into the potential energy of the charge. Okay, so what's the difference between potential and potential energy? Potential, the difference is where the energy is stored. In the case of potential, the energy is stored in the electric field. In the case of potential energy, the energy is stored in the charge. That's it. So how do you charge something up? You have to just put the charge in this energized field. So you have to create a region of potential difference, and when you place the charge in it, the charge becomes energized. And then what happens if you let the charge go? Well, the charge got potential energy already. So what do you think is going to happen? There's an electrostatic force acting on it. That's a conservative force. So which means this potential energy is going to turn into kinetic energy. So which means the charge's potential energy is going to diminish, and its kinetic energy is going to go up. All right, so this E and that E are not the same. This is the electric field. I end up putting N, subscript N at the bottom to denote that this is electrostatic. This one is energy. This is the electrostatic force field. So the mechanical energy is constant. So potential energy goes down, the kinetic energy goes up. All right, so put differently, electrostatic force acting on the charge is going to induce a force on it. Electric field acting on the charge will induce a force on it. And the force is going to make it, it's going to cause it to accelerate. Constant electric field, constant force, constant acceleration. Or put differently, force causing displacement represents the amount of work done by a conservative force field. And the conservative force field is going to reduce the potential energy and increase the kinetic energy of the system. So you can look at it from a kinematics perspective. All right, problem number 2. All right, this is the setup that I'm using. All right, so we're dealing with a TV tube within which you have the capacitor. This electron is going to be accelerated in the forward direction through a potential difference. It says 5,000 volts. I'm using an actual number, so it's going to be 25,000 volts. So what is it that we're interested in? We are interested in the speed of an electron as the electron is just leaving this opening right in the middle. And so what's the speed? Each and every single electron is going to leave this hole at the same speed. So how do we figure that out? All right, so they work down by a conservative force. Conservative force is acting on a charge or a mass. It's going to reduce its potential energy and turn it into kinetic energy. All right, so that's what a conservative force does. Okay, this is a fast review before we do the problem. All right, so the work is going to reduce the potential energy of the charge with a mass and convert it into kinetic energy. All right, so this got potential energy. When you let it go, what happens is potential energy is diminishing in this direction. It's going to turn into kinetic energy. All right, so this is, all right, so potential, if there's a potential difference, if the energy is stored within a region when you place a charge in it, it's going to have potential energy. So what happens to the potential energy of the charge? All right, so the potential represents the amount of energy stored within the electric field between two opposite charge regions, separated through a distance of r, distance r. And so, all right, so when you, all right, when you take this equation and then isolate V, what it says in essence is the voltage is the amount of energy stored within the strength of the electric field. And this represents the potential energy. Potential energy is the amount of energy stored in the charge. So this represents voltage is the same as amount of energy per charge available or stored in the electric field. That's what it means. All right, that's just too much right now for you guys. So let's just move forward. Let's just work on the problem. That makes it way too abstract. So let's just get up there slowly. All right, problem number 2. All right, so potential difference between the plates, 25,000 volts. So we want to know how fast electrons are moving when they hit the hole in the positive charge plate. All right, so that's an electron gun. All right, so voltage to potential difference in this case. Voltage to potential difference is going to be 25,000 volts. Electron is the one that's going to be accelerated. It's the unit charge. So the speed in terms of meters per second. If the number is small enough, we'll express it miles per hour. If it's too fast, we'll express it in terms of the light speed. So this is coulombs, and this represents the light speed. All right, so this is lowercase c, this is capital C. Once again, this setup, this is a negative charge region, this is a positive charge region. So the electrons will accelerate in the downward direction. So this represents a potential difference. This is a low potential region, this is a high potential region. Initial speed of the charge, the final speed of the charge. So this capital V, these are lowercase v's. Initial speed of the electron is 0. Electric field is in the upward direction. So the electric field acting on the charge will induce a force on it and make it accelerate in the downward direction. All right, so electric field, so this is a region of potential, so which means that it's an energized region. When you place a charge in it, it's going to have potential energy. All right, so that's what I'm getting at. All right, so conservative force field acting on the charge is going to act to reduce its potential energy, and it's going to turn into kinetic energy. All right, so potential energy of this charge is, you know, the potential difference, right? So the region is energized, and as soon as you place a charge in it, now it's got potential energy. So the charge is placed within this region, it's got potential energy. So what happens is potential energy is going to go down, and it's going to turn into kinetic energy. All right, so this is the potential energy. All right, it's going to reduce the potential energy. Guys, potential is like the height difference, okay? Which region is positive, which region is negative, doesn't matter. So you can effectively get rid of the negative sign. I don't want to just focus on the meaning of it too much because we are swimming in too much abstraction right now. Because this negative sign is going to disappear, and then it'll become obviously at some point that this negative sign, this is more of a matter of expression than something that you use in your computation. What this means is conservative force reduces the potential energy, hence the reason why I have a negative sign up front. Increase the potential kinetic energy, and there would be a positive sign up front. Okay, so it's more of an what's going on with this term and with that term. Aside from that, it doesn't have any significance. I would not carry this into my computation. All right, so here's the potential energy of the charge. So what happens? This potential energy is going to turn into kinetic energy. That's it. All right, so instead of using Q times change in voltage or potential, I'm just going to say voltage. I'm going to get rid of delta as well. Q becomes E. All right, don't worry about the sign in this case, because we're dealing with scalars in essence. These are, we're dealing with energy right now. So let's not worry about anything else right now. All right, so initial speed is going to be 0. So we want to figure out the final speed. All right, so I think we need to know the mass of the electron. We got the charge of the electron. All right, so I'm making a point that, hey, don't worry about it. This one is negative, this one negative. You can just cancel them out if you wanted to, but I don't usually care, because you have to figure out which region is positive voltage, which one is negative voltage, which one is high voltage, which one is low voltage. As long as you're looking at voltage difference, it doesn't matter which one is high, which one is low. You can just say it's going to be a number. All right. I mean, if you're 7 feet tall from top to bottom or bottom to top, it makes no difference. You're still 7 feet tall. That's what it means. Voltage difference is like the height difference. I don't care which reference frame you're measuring with. All right. So, and that is going to give you a number, whatever that number is. Okay, so that when you do the work, I think you end up getting 95 millimeters per second. And that converts to check to see if that makes sense. Okay, so I'm not interested in numbers per se right now. How the concept develops. Okay, so let's get back to the relationship. So electric field between two opposite charge regions, obviously, separated through a distance of r, is going to give you the voltage or potential difference. So that represents the amount of energy within that region. Okay, so let's go back to the same problem, and this time let's figure out the strength of the electric field within this region. All right, once again, this region is charged up to 25,000 volts, so potential difference is 25,000 volts. Plate separation is going to be 1.5 centimeters. So what's the strength of this electric field within this region? Okay, these are simple enough problems. And these are also really useful problems. Once again, the voltage potential difference is again 25,000 volts. Separation distance is 1.5 centimeters, so expressed in terms of meters. So what's the strength of the electric field within that region? All right, so it's the same region that we are dealing with. Now we are trying to figure out the strength of the electric field within the separation distance. All right, so we know the voltage difference. We know the separation distance, so isolate E. And then plug the numbers in. All right, and then when you plug the numbers in, this is what you end up getting. All right, it's almost 1.7 million newtons per coulomb. All right, so now what I decided to do is I'm going to go back to problem number 2. I end up solving this problem. using the conservation of energy. Now I'm going to bypass the conservation of energy. I'm going to try to do it using the equations of kinematics. Okay, so you could appreciate the difference in elegance. Okay, so I'm going to go back and then redo this problem using the kinematics equations. So you can see how powerful the conservation of mechanical energy is and how powerful the concept of potential and voltage is. All right, so here's the strength of the electric field. All right, we just computed the strength of the electric field in problem number 4, okay? And here's the electron. Initially, it's not moving. So what's going to happen is it's going to, under the influence of the electrostatic force acting on the charge, it's going to accelerate from 0 to God knows what through a separation distance of 0.015 meters. All right, so I decided to circle back to problem number 2 with new information, and I'm going to check to see if I'm going to come up with a different number for the speed. All right, so whatever the speed was, I forget the number, but it's not that important. Okay, so now we will get to use the equations of kinematics. Okay, so for speed, the question is, do we get the same number? Okay, now that we know the strength of the electric field, which we didn't before, but we do now. All right, so the way to do it is, as this electric field acting on the charge is going to induce a force on it. The force is going to cause acceleration through this distance. All right, so R, I'm just going to make R X because I want to use the kinematics equations. All right. All right, so I'm looking at what's given, and I want to know what the final speed is. And I know I can figure out the acceleration because this electric field is going to induce a force on the charge. The force is going to accelerate. So the only formula that I can use for the final speed is the third one. I cannot use the first and the second one because I don't know what time is. So the final speed, the only one that I can use is the third one. All right, so that's what I'm going to do. All right. Initial speed is 0, so that's going to drop out. All right, so here's the final speed. Acceleration is not given, but I know how to get the acceleration, thanks to Newton. Acceleration is caused by a force, obviously, and the force comes about because of the electric field acting on the charge. All right, so force comes about because the electric field is acting on the charge, and the force is what causes acceleration. All right, so force is what causes acceleration of this mass. All right, so solve for A. All right, so force divided by mass is going to be your A, so do a back substitution. All right, we know the charge, so that's the unit charge for the electron. We know the mass of an electron. We know the strength of the electric field. And then you plug the numbers in, which I'm not going to more than likely because it's a lecture. And I'll get the same number. Okay, guys, notice that if you're using kinematics, you have to keep track of a lot of different variables. Now, you need to remember that the electric field has to be constant. And you know it is constant because, you know, these are metal plates. There's going to be a uniform distribution of the charges. And then you have to, in real life, you would have to come up with an expression for the strength of the electric field. You have to use the Gauss's law. Electric field acting on the charge is going to cause a constant force. If the force is constant, acceleration is constant. If the acceleration is constant, you can use kinematics equations to actually figure out the final speed. You know, there's like 4 or 5 different concepts you have to use in order to solve this problem effectively, versus the conservation of energy. All right, so there's voltage difference, which implies that there are 2 regions of opposite charges. Energy is going to be stored in between, within that gap, separation distance of R. Place a charge and it's got potential energy. So what happens to potential energy? It turns into kinetic energy. That's it. Conservation of mechanical energy, and it becomes real easy if you understand voltage or potential. Voltage or potential means that energy is going to be stored within that region. All right, and you energize the charge by placing a charge into that region, within that region. That's it. And it's a powerful, powerful concept. All right, so gravitational potential energy is the stored energy. It depends on the height. Okay, so I'm just gonna. This is a very dismissive way of saying it depends on the height, location. Okay, fine. So it just represents the amount of energy available. All right, so how do you store energy? You just lift something up. That represents the amount of work done against gravity. What you're displacing is the weight of this object. The object gets displaced against gravity. All right, so its weight gets displaced. As a result, it's got energy. All right, so that's a little bit more accurate statement form. All right, so what's gravitational potential? Ignore that. We'll get back to it. What's electric potential? Voltage, that represents the amount of energy stored within the electric field between 2 opposite charge regions. All right, high voltage is a positive charge region, the low voltage is a negative charge region. The V represents a voltage or potential difference between these 2 regions. It represents the amount of energy stored within the electric field in that region. Potential energy is the amount of energy stored within the charge. All right, so how do you store energy in the charge? Well, there are 2 ways of doing it. You can go blah, blah, blah. You have to bring this positive charge near a positive charge region. You have to do work against a conservative force field, and then you can keep talking forever until somebody falls asleep. Okay. Or the only thing you have to do is just drop a charge into this charge, the energized region, so the charge becomes energized. So V indicates that this is an energized region. So energy is already stored within this region. So if you drop a charge in it, the charge also becomes energized. Now it's got potential energy. So what's the difference between potential and potential energy? Potential is the amount of energy stored in the electric field. Potential energy is the amount of energy stored in the charge. All right, so it depends on where the energy is stored. In the case of the potential electric field has the energy because it's got the capacity to apply for something and make it move. That's what it means. And in the case of potential energy, the charge has the stored energy. That's it. So how is the potential related to the strength of the electric field? The stronger the electric field has, more energy is stored in it, which means that it can apply a stronger force and make things go faster. All right, so that becomes high voltage. All right, so the stronger the electric field is, the more energy stored in it. Larger the voltage difference is, larger the voltage is, the potential difference is. All right, so how's the potential related to the separation distance between two opposite charge regions? All right, for a given electric field strength, larger the separation distance is, the more voltage, the larger the voltage is. Okay, so what is the meaning of that? I'm just gonna mumble something. Eventually, regardless of what I say, you won't probably get it right away, but you will appreciate it later on. And hopefully while you're watching it, you'll focus on it a little bit more next time. Guys, electric field strength, electric field acting on the charge is going to cause a force on it, which means that the charge is going to keep accelerating, right? Longer the distance of acceleration is, the faster it's going to move. That's what it means. Okay, because the same force is going to keep acting on it. So which means that the larger separation distance is, the faster the charges are going to move. That means that there's more energy stored within that region if the separation distance is larger. Okay, so that's one way of looking at it. All right. Lightning phenomenon. All right, one of the things you will notice for lightning is hair. If you see someone's hair rising up in this fashion, her brother thought this was funny, so he snapped a picture, and then shortly after they left, the lightning struck. One person died, 2 people got injured. All right, this is one of the signs that you may be about to get struck by lightning. So the question is, what's causing the hair to rise up? The reason why that happens is because, you know, the ground becomes polarized, so ground becomes positive charge. Your body will become polarized, so top of your body becomes positive.
I wanted to show you that electricity can actually be useful. So when my young friend here told me that she wanted her hair teased, I thought maybe I would do it on this Van de Graaff machine. You know, this won't hurt a bit. There we go. Now watch what happens when I turn it on. You see that? Electricity can be absolutely hair-raising. She wanted to know how much this would cost, but I told her that by the time I was finished, there'd be no charge.
Somebody really enjoyed that joke. Got to be a physics student. Evidently, the guy has a deeper understanding of physics. So what's causing hair to rise up? Well, what's happening is your body is going to become, top of your body is going to become polarized. It becomes positive charge. So light charge will repel. In essence, that's what you're looking at. All right, which also means that the streamers from your body start to make connection with the step leaders from the cloud. So you have to just probably have a minute or less before you get out of there. All right, so let's discuss the lightning phenomenon. High ground versus the low ground. Why is it that the high ground is more likely to be struck by lightning? All right, so this thing is assumption sensitive. All right, number one, the friction among ice particles is the reason why the ionization happens. For unknown reason, the top of the clouds will become positive charged, the bottom negatively. And the ground, which is initially negatively charged, will become positive charged through polarization. All right, so the negative charge will start to move towards the ground because of the attraction between opposite charges. Positive charges will start to go up towards the clouds. Whenever the high concentrations meet, it's known as lightning, so there's going to be a discharge, which means that the charges will become neutralized. That's what it means. All right. Separation distance R1, high ground to the clouds. R2 is going to be low ground in the clouds, between the low ground and the clouds. Okay. So what I'm going to do is come up with a bunch of numbers. Number one, lightning usually happens, according to one source that I found, around 10,000 newtons per coulomb. It's not 3 million. Okay, 3 million is, I don't know where these books are getting that number from. That's the ionization of air. Okay, that's sort of, I don't see that. That's complete nonsense. All right, so here's the measured value for the strength of the electric field. So that's 10,000 newtons per coulomb, which is a measured value during a lightning strike. Okay, I'm just gonna make up some numbers. High ground and clouds, I'm gonna make it 100 meters because it's a 1 football field in length, more or less. We just had Super Bowl. You can kind of visualize that distance. And the low ground to the clouds is going to be 10 football fields in length. It's 1,000 meters. Okay. And then what I'm going to do is I'm going to look at the voltage difference between these regions. All right. So voltage difference is going to represent the amount of energy stored. All right. Hold on, guys. Am I going? Somebody commented, but I can't get to the comment, so let me just. Oh yeah. Okay. Absolutely, yeah. Alex, it's gonna be available. I expect you guys to watch this and watch this over and over again. So this lecture is gonna be available. So keep yourself icons on that. Okay. So what I'm looking for is what's the amount of energy stored within the electric field within this region versus that region, and what does it even mean, even if you did find the voltage difference or the potential difference. All right, let's just do it blindly, like the way you would solve physics problems from physics books. All right, just like pretend that this is math. All right, so which means that look at the voltage or voltage difference. Strength of the electric field is going to be the same in both cases. Separation distance are different. All right, so 10,000. This should be 100. All right, so I made a correction. So this should give us 1 million volts. All right, and all right, so the other one is 10 times larger, so it's going to give us 10 million volts. Okay, so what does it mean? That means that the amount of energy stored between high ground and clouds has got to be 1 million volts, and the other one is going to be 10 million volts of energy, joules of energy per coulomb of charge. That's what it means. So here's where it gets kind of weird. This is what you don't get from these textbooks. Based upon this, I say, oh, it's going to strike high ground. I look at this number immediately. I go, oh, okay, so it's more than likely it's going to strike high ground. In fact, if physics is 100% accurate in everything that we do in physics, which is not, but let's assume that I'm cocky enough to think that, which means that 100% of the time the lightning should strike high ground because that's what this number says. Okay, so the question is, how do I go looking at this number and drawing that conclusion from that? The reason why I'm able to draw that conclusion is because I know what voltage represents, guys. The voltage is now the third interpretation of voltage. I give you like 2 interpretations, not the third one. Okay, this is, again, what this represents is the amount of energy required for the charges to jump that gap. That's what it means. When the voltage difference reaches this value, the charges will have enough energy to jump the gap, guys. That's what it means. All right, so which means that the charges will have enough energy at 1 million volts to jump the gap sooner than at 10 million volts. All right, so which means that the potential difference is going to reach 1 million volts before it reaches 10 million volts, which means that the charges will have 1 million joules of energy per coulomb of charge before they attain 10 million joules of energy per coulomb of charge. All right, so which means that at a higher altitude, when the separation distance is smaller, the charges will have attained enough energy to jump this gap. But the problem with that logic is, though it is correct, and it's not correct 100% of the time. All right, so instead of lightning hitting high ground 100% of the time, it does something weird. All right, so it hits high ground instead of 100% of the time. It hits high ground, I don't know, I'm just going to make something up. 70% of the time, it's the low ground, like 30% of the time. Okay, so why is it that the physics not working out? I got news for you guys. The physics is working out just fine. Physics is still really, really accurate. What's not working out? The reason it seems like we end up getting something weird is because of the assumptions that we kept making. Okay, guys, one of the assumptions that we made is when the electric field strength reaches this value, that becomes a favorable condition for lightning. But this electric field strength depends on the charge distribution. Charges are not uniformly distributed, not underground, not under the cloud. Okay, it's not like a capacitor, parallel plate capacitor. Okay, if the charge distribution is positive charge distribution, concentration of positive charges is strong enough here, and the concentration of negative charge is strong enough so that the electric field strength is 10,000 newtons per coulomb, then okay, so these charges are going to jump. But some concentration of the charges, sometimes positive charges are stronger here, the negative charge is stronger here, and then boom, it's going to end up striking low ground. It depends on the concentration of charges, the charge density. Okay, you don't have a uniform charge density here. And the funny thing is, you cannot eyeball this, all right? You can't say, hey, well, it seems like the charge concentration is larger here and larger here, so you can't really eyeball this stuff. All right, and that depends on, because the charge distribution is not uniform, sometimes it ends up hitting the low ground because you end up getting a higher positive charge concentration here and higher negative charge concentration there. And it's the same logic, so which means that these charges will have to wait until they have enough energy to jump this gap. Okay, so classically, that's, all right, this is my old school, and the distance between this building and that building is a mile. I mean, this building goes up 1,450 feet. The top of the tower that you're looking at, the antenna, this is 1,500 feet tall. And this is, comparatively speaking, this is not a tall building, and this is the building which is getting struck by lightning. The reason is because somehow this building has a much higher density of positive charges, and obviously the clouds up above have much larger density of negative charges, and so they connect. And this is what happens. The lightning is born.
One of the most surprising discoveries is that lightning is blind as it streaks towards the Earth. It is only in about the last 100 feet that it senses the Earth's electromagnetic field and selects a place to strike.
when it does come down, you can see in this picture here that it's coming in little 50-yard steps, 50-meter-long steps called step leaders. It keeps coming down toward the ground in this part of the channel. This is the one that made it to ground. As it comes closer to the ground, when it gets down to this last little part here, this is a really important part. This last 30 to 50 yards, it looks for something to hit just in this little area.
As the stepped leader streaks towards the Earth, anything sticking up, buildings, trees, even people, send up positive streamers in response. When they connect, lightning is born. Negative electrons are discharged to Earth, and a positive charge travels back up the cloud at 60,000 miles a second. Here, 2 streamers leave the tree, but only one successfully connects with the stepped leader. The telephone pole has also launched a streamer, a failed lightning bolt. Packing up to 100 million volts of electricity, lightning has the power to explode walls of concrete and destroy electrical systems. Each bolt is 5 times hotter than the surface of the sun. Exposure to its power for a fraction of a second can be lethal. It was a beautiful afternoon in Colorado, and hundreds of people were out soaking up the summer sunshine. But out of the clear blue sky, nature played a cruel trick.
It happened on a day when there wasn't a cloud in the sky. It was a clear blue sky when, from out of the blue, a bicyclist was struck by lightning. It seemed mysterious to us because where was the cloud from which this lightning originated? This was the first opportunity we thought we had to investigate it, to find out where that cloud was. And to do that, we sought the help of Global Atmospherics in Tucson.
But would Global System be sensitive enough to pinpoint this mysterious bolt?
We went back and plotted the data for the 3-hour period around the time when this event happened in Vail. If we look here at the screen, we can see the flash over Colorado. And in this case, there was only one flash within 20 miles of this particular location in Vail. This is definitely the one that struck the person.
They found that the single lightning strike in this county at that time of day, on that day, originated in a cloud 10 miles on the other side of this mountain. That cloud was not visible in the valley. So there was no reason for the people, including our patient, to seek shelter. But it is not unknown for lightning to travel some distance, including, in this case, 10 miles, in other instances even more, before it takes a downward dip to reach the ground.
They may appear to come out of the blue, but they are coming out of a thunderstorm for reasons we don't understand. The lightning sometimes will come out sideways from the cloud rather than down below it.
Lightning is capricious. Lightning, which is a beautiful phenomenon of nature, and we all can sit and watch it, but it also can be one of the most cruel phenomena of nature. And this one was particularly cruel because it was hidden.
Lightning is among the biggest natural hazards, killing more people each year in the U.S. than hurricanes, tornadoes, and earthquakes. The paramedics in Lightning Alley are only too aware of this. This storm has already claimed its first victim. Who will be next?
Actually, lightning generates tremendous amounts of heat, and with that comes instant water vaporization, which with wet clothing results in an explosive appearance of the clothing. It becomes shredded, metallic objects become fused, such as zippers. And surprisingly, with all this heat that's being generated, there are relatively few burns and some singeing of hair. What we also know now is that there's a tremendous amount of explosive effect or mechanical effect of the lightning that will cause eardrums to rupture, can cause bruising of the heart, and contusions of the brain, as well as some skull fractures.
With this sort of power, it's surprising that anyone survives. It's a hot, humid summer's day. Thousands of people are gathered at RFK Stadium for the Freedom for Tibet concert. Suddenly, disaster strikes. One young woman has been singled out from the crowd by a lightning bolt, stopping her heart and paralyzing her lungs. 3 years later, the victim has made a remarkable recovery.
My sister Amanda and I were sitting around here when we came to the concert, and it was a nice day in Washington, which is unusual in June. It was sunny and not too hot, and we were watching the show, and all of a sudden, a huge cloud came out of nowhere without any rain, and a bolt of lightning came out from the sky and hit me right on my head. I was thrown onto the ground, and 2 people near me in the crowd rushed over.
Luckily, one of those people was an off-duty doctor.
She was bleeding from her lips at the time, so we wiped the blood off of her lips, and we started CPR right then. And we all started chest compressions at the same time because she didn't have a heart rate. And it was about 10 minutes after I initially seen her that she regained a heart rate of her own. Without the CPR, she probably would have been brain dead.
Lisa had taken a direct hit from the lightning. As she was rushed off in the ambulance, the medics didn't know she would survive. But why had Lisa been selected from a crowd of over 66,000 people? She wasn't the tallest object. There was the top of the stadium. Even the musicians on the elevated stage would have been an easier target. A discovery made 60 years ago may hold the key to Lisa's mysterious attack. Throughout the 1930s and 40s, the General Electric Company studied the way lightning bolts hit the Empire State Building in New York. They found that the Empire State was hit on average about 23 times a year. But when the team went back and analyzed it appears that sometimes a lightning bolt is too weak. It appears that sometimes a lightning bolt is too weak to trigger a streamer until it gets much closer to the ground. By this time, it may have already missed the tallest object.
This makes it possible for a leader, if it's very weak, doesn't have much charge in it, to propagate down towards the ground parallel to, say, a tall building like the Empire State Building. And if it always stays 50 or 60 meters away, it could come all the way down near the bottom before a leader comes off the side of the building at some random point and meets it, and then the lightning attaches to the side of the building. So the tallest thing around is not always what gets hit. Leaders without much charge on them can work their way in between buildings, or can hit the bottoms of trees, or can do things that you wouldn't think otherwise would occur.
The bolt that struck Lisa may have sent down a weak stepped leader, which sneaked past the top of the stadium and the stage. Other people in the audience, as well as Lisa, would have sent up streamers to try and trigger the lightning bolt, but as it zigzagged closer and closer to the crowd, it was only Lisa's streamer that made the fateful connection. As the lightning flashed over Lisa, the searing heat caused second and third degree burns over 20% of her body.
These are the clothes I was wearing when I was hit by lightning. My mom kept them so I'd understand the sheer force of what I survived. The shirt, you can see, was just totally blown away. And my bra, which had a metal underwire, was melted, the metal, and it caused a third-degree burn under my one breast. Something I never understood, though, was how this could have happened if I was wearing 2-inch thick rubber sneakers. I even asked the doctors in the hospital when I realized what happened to me. I later learned that sneakers aren't going to save you if there's a lightning bolt anywhere near you.
Lightning hits the Earth 100 times a second. In the U.S. alone, there are more than 25 million cloud-to-ground strikes each year. About 1,200 of these will hit people, and 100 will be fatal. The reason why so many people are struck each year is that our fluid-filled bodies provide excellent pathways for electrical charge.
The thing about the body is that it's a very good conductor of electricity. Most of the fluids in the body are very salty, and so they conduct very well indeed. And I can show you that on this ball here. These little streamers are just like lightning, except they're very, very small in the way of current. And you can see just how concentrated the electricity becomes. If I put my whole hand, you can see how most of the streamers concentrate around the hand. And it's being conducted down my arm and through my body and away to Earth. Now, perhaps I can make that a little plainer by using this fluorescent tube, and I can conduct current through the fluorescent tube. If I put the tube like so, you can see current is being transferred through here, along through my right arm, and down and away to Earth. If I do it on this side, the same happens, but on the other half of the body.
The same property that allows us to conduct electricity from the plasma ball also makes us living lightning rods. 3 years later, Lisa is back to normal.
When I feel like I'm taking life for granted, I take a step back and I go, you're extremely lucky, because there's a huge chance that you wouldn't have been here, so enjoy the day.
Lisa was very lucky. Only a small number of people who suffer a direct hit from a lightning strike live to tell the tale.
Okay, so let's go over some of the stuff.
Target. And if it always in the state.
By lightning. My mom kept
But as it zigzagged close.
Okay, so tall structures aren't the ones that get it by lightning 100% of the time, because the charge distribution is not uniform. I think
closer and closer to the crowd.
aren't going to save you if there's a lightning bolt anywhere near thick rubber sneakers.
Sneakers will not help, right? Your body becomes polarized. So it makes no difference that you're wearing sneakers or something else. And besides, she's already sitting on the ground, so it makes no difference. For whatever the reason, these streamers from her body became
I even asked the doctors in the hospital when
connected with the step leaders from the class, and that's exactly what happened. So it was just a random thing that happened. All right, except the weird part of it is she survived. Roughly about 1 in 12 who get struck by lightning end up dying. That's a small number, but a lot of it is because those are usually sight flashes. They're not direct hits. It's kind of tough to survive a direct hit.
Yeah, a way to Earth, way of current.
Now, it's an interesting thing that's...
The reason why so many people are struck each year.
They're very salty, and so they...
Okay, I love this one. These are, here's a plasma ball. It's generating its own streamers, okay? And then streamers are connected to the charges coming from your body, so you end up getting this large charge distribution on it. If you want to know whether or not you're going to be struck by lightning, there are a couple of things that you could do. One is really nerdy. I mean, if you really value your life to an extent that you don't want to get struck by lightning, get one of these fluorescent bulbs, just put them on your shoulder and start walking around. This lights up, which means that you have about a minute before you're struck by lightning. Okay, which means that the streamers from your body is making contact with the step leaders from the clouds. Or, obviously, you don't want to look this goofy. You just get a pocket size if your crutch lights up, which means that you're about to be struck by lightning. There's stuff available online that works on the same principle, give and take. It's some kind of a pocket vibrator. It starts vibrating. when the streamers make contact with the step leaders from the clouds. Okay, so that's the whole idea. Or if you see somebody's hair rise up or whatever, which means that that region, streamers from that region is making contact with the step leaders from the clouds. So just get out, get into your car or something. All right, so electric potential, the meaning of the electric potential. This represents a potential difference, which means that one region is going to have high potential, the other region is going to have low potential, which means that one region is going to be positively charged, the other region is going to be negatively charged. That also means that the electric field in between within that region is going to be energized. So the amount of energy stored within that region is the amount of work, the capacity to do work creating a charge. So the voltage or potential represents the amount of energy stored within the electric field per charge. That's what it means. All right, so the voltage or potential is the amount of energy stored within the field, potential energy stored within the field per charge is the voltage or potential. Okay, gravitational analogy of potential difference is the same as height difference. Okay, so it's the same as elevation that you're looking at. You got two masses, they're at the same elevation, which means that they have the same potential. All right, so the potential difference is the difference in elevation. This is high voltage, this is low voltage. And the masses will move from a high voltage towards the low voltage. Charges will do the same. All right, so the charges that we're referring to are usually positive charges. Positive charges, when there's a voltage or potential difference, when they're free to move, they will always go from a high voltage region to a low voltage region. Just like the masses go from a higher elevation towards the lower elevation under the influence of a conserved force field. All right, so elevation is the same as voltage from the perspective of gravity. All right, so every single point is going to be at the same elevation within the circle. So every single point is going to be at the same voltage within the circle. So this circle represents everything within the circle. Within this height represents an equal potential surface. These are known as equal potentials, which means that every single point is going to be at the same elevation. Likewise, this one and likewise that one. If you have a ball, if you let it go, it's going to move from a region of high voltage towards the low voltage. It's just going to roll down, right? And gravity always points from a region of high voltage towards the low voltage. Yeah, so that's the terminology that we will get to use. The relationship between voltage and force, or force field, is what we're going to explore right now. All right, so 25 meters is the altitude that we're looking at. Every single point within the circle is going to be an equal potential, the site. And you got 20 meters, 15 meters, and 10 meters. So you have these equal potential surfaces, or these are the equal potential lines that you're looking at. Okay, so that's the gravitational perspective. Likewise, you have a positive charge. Positive charge represents a region of high voltage. All right, so this is your hill. Okay, so every single point around this region is going to be at the same height. All right, so which is like the hill, and you go away from the top. So this is going to be a lower elevation. This is going to be a lower elevation, and so forth. So here's one equal potential. Here's a second equal potential, the third one, and the fourth one. All right, so that's the expression that we will use. All right, so these are equal potential surfaces, 1, 2, 3, and 4 that you're looking at. Regardless of where you are on this equal potential surface, voltage and potential is going to be the same. All right, so moving a charge on an equal potential surface is not going to change its potential energy is not going to change. That's what it means. But if you're moving a charge between two equal potentials, what's happening is its potential is going to change, its potential energy is going to change. All right, so its potential energy can turn into kinetic energy if it's done, if the force is a conserved force field, for example. Okay, so it doesn't matter that you're moving the charge from here to there in a straight line or meandering around. Once again, path of motion is not going to matter. The only thing that's going to matter is the initial and the end points of this motion. All right, so positive charge, positive charge, negative charge, high voltage, low voltage, high voltage region, the low voltage region, high potential, low potential. Okay, they mean the same. Okay, so the green dots that you're looking at, these are equal potentials. You got one equal potential here, and you got a lower equal potential, and you're at a lower equal potential. All right, so this almost represents a hill, and you got a negative charge region, so this can be low voltage. Okay, one thing that I want you to notice, and that's important, these red lines that you're looking at, these are the electric field lines. Electric field starts at the positive charges. So the positive charges are the emitters, radiators, transmitters, and negative charges are the receivers. Okay. Potential is something that you can measure. Okay, we're not able to do that because of COVID, obviously. So I have to find some labs that you can do or watch online. So at least you know what a voltmeter looks like. You can actually measure the voltage near a charge. Okay, so when you measure the voltage near a charge, and every single point which has the same reading is going to be on an equal potential surface. So we would normally do a lab something like that for similar to this. So we measure the voltage, and then we would just connect the dots in essence for the dots that have the same value. So you get these circles around charge regions. Electric field is something that you kind of draw. Okay, this electric field is some kind of a visual apparatus, or more like a visual conceptualization that Faraday came up with. Right? The reason why he came up with this is, as you will find out later, because the guy couldn't do math. Right? He would do everything visually. And that's the reason why everything that we've been doing so far are extremely visual. You can draw out the electric field lines, and they're fairly easy to draw out because the electric field lines will always be 90 degrees to these equal potentials. And notice that the electric field will always point in the direction of the diminishing potential, all right? Because potential is going to diminish away from the positive charge, the electric field points away from the positive charge. So the electric field lines will point in the direction of the diminishing electric potential. All right, so here's the equation for it. I'm going to give you a derivation of it shortly. All right, so here's the strength of the electric field. Okay, so the electric field is going to point in the direction of diminishing voltage or potential. So the voltage is going to change in the direction that the electric field points radially. That's what it means. All right, so here's a positive charge region. The electric field is obviously pointing away from the positive charge region. And so which means that the strength of the electric field is going to be stronger here. And then as it starts to move away, it gets, in essence, it gets weaker. That's what it means. So the amount of energy stored in the electric field here is going to be larger. It gets smaller, as you start to move away from the source radium. All right, so that's the meaning of positive charge region, the negative charge regions. Here's your separation distance. This represents the amount of energy stored within that region. Okay, and so the separation distance is expressed in terms of a differential, and then you express it in terms of an integral, and then it gives you the potential difference or voltage difference. All right. Okay, so let's take a look at an actual derivation for this one. All right, calculating potential from the electric field. All right, so the work done by a conservative force is going to reduce the potential energy of the charge. All right, so which means that if you place the charge inside that region, electrostatic force is going to act on it, and it's going to reduce its potential energy and turn it into kinetic energy. That's what it means. All right, so the force is going to be generated by the electric field acting on the charge. This is Q naught, is known as a test charge usually. All right, so this is going to represent the amount of work done by a conservative force field. So what I'm going to do is just get rid of the net charge on both sides. Okay, so the work done per charge equals to the electric field times the separation distance, which is the same as the voltage or potential difference. So the amount of charge, the amount of energy per charge is the same as voltage or potential. Okay, so notice what's happening, guys. This is one of the things that I want you to see. I give you a lecture from Yale, and this is the sort of stuff that the guy does. Yale guy does. I love the guy. He's an amazing lecturer, except he usually traditionally the approach to physics is extremely mathematical. Okay, he talks about it and then he explains it, and next thing you know, he's talking about voltage and potential difference. The voltage and potential difference in this case is the same as the energy per unit charge. How much potential energy is changing per unit charge? That's what the math says. Everything comes out of the mathematics. You do a little bit of algebra, but notice that when it's explained to you in this fashion, derivation after derivation, you can kind of see the math, but you don't really get a grasp of the topic. All right, kind of the concept gets lost in the mathematics. Okay, I gave you the lecture presentation so you could see how it is done at Yale. Okay, most universities more or less the same thing. And usually everything gets done in a very mathematical sort of way. At the end, you come up with this expression, and the meaning of this expression is exactly what I said. All right. Okay, so sometimes I skip the derivations because they're not that important. Derivation is the same concept that I'm telling you, except now through a derivation, we come up with a mathematical expression that we could use. Okay, so the derivation is expressing the ideas that I'm expressing in the formal mathematics. If I were to give you the ideas through derivations, you're not going to learn anything. It's one of the worst. If you don't get it in English, you're not going to get it once somebody explains it using highly convoluted mathematics. Okay, so what this means at the end, okay, so entire equation boils down to this stuff, which means that the voltage and potential is going to change in the direction that the electric field is pointing. So, which means that the voltage and potential is going to diminish in the direction that the electric field is pointing. That's what it means. All right, so the electric field is going to point in the direction of diminishing potential. All right, so you can do the derivation, this and that blindly, and that's what a lot of the instructors do. And then the physics is lost. All right, so I'm just going to show you some of the derivations as we go along. Okay, so at least I want you guys to kind of get used to it. You're not required to be able to do these derivations at this level, but when you're taking this course over again, which you will have to, regardless of what you're majoring in, E&M, electricity and magnetism for engineering majors, a lot of what you will do is going to be similar to these derivations. All right, not these basic derivations. So this means that conservative force acting on a charge in this case is going to reduce its potential energy. So this is change of potential, can be expressed in terms of a derivative of a potential. All right, so the work is force causing displacement. You do a back substitution. And then force is the same as force is caused by electric field acting on a charge. I'm giving exactly the same derivation. Except now this is a little bit more exciting because we got the green color. And normally the instructions will spend 30 minutes talking about it. And then now what we need to do is the amount of energy per unit charge, we will call this the potential difference. So change the terminology. Oh my God, this is so exciting. And then that's it. It's exactly the same derivation. And the meaning of it is, which means that the electric field is going to point in the direction of diminishing potential. This is kind of neat. All right, aside from that, there's something interesting that comes out of it, which means that if you know the potential within any region, you can figure out the strength of the electric field within that region. Okay, it's got some powerful mathematical implications. I think I'm probably going to do one problem regarding this week, because I want you to know how to use this formula. All right, so if you know the voltage potential in a given region, instead of using all that vector calculus that we were using, we can figure out the electric field strength from X direction, Y direction, Z direction. It doesn't matter what the direction is. And this is a powerful mathematical technique. So I'm going to come up with a formula for that.
What does the electric field for this potential look like? Because it takes no work to move a charge along a curve of constant potential. There's no component of field in that direction. So the field is perpendicular to each equal potential at every point. And that's how it assumes its familiar shape. What does the electric field for this potential look like?
All right, let's go back. High potential, low potential. Electric field lines will point from a region of high potential towards the region of low potential. That's what it means. High potential is like a hill, and low potential is like a well that we're looking at. Okay, so a couple of things. Now let's come up with some formulas for potential, expressions for potential. All right, so what is the electric potential due to a point charge? Okay, so we'll take a look at the electric potential due to a point charge. So this is our point charge. And we'll try to figure out the electric potential at point P. All right, so that's what we're going to be looking at. All right, if it's a positive charge, it's like climbing up a hill. Positive charge is going to give you a positive potential, which means that if you bring a positive charge near, you have to apply more and more force. It's going to be more and more difficult. From a gravitational perspective, it's going to feel like climbing up a hill. That's what it means. So the positive charge is going to give you a positive voltage. So this is a high voltage, high potential region. Gravitational analogy is going to be a hill. Obviously, low voltage or low potential is going to be a negative charge region. Gravitational analogy is going to be a well that we're looking at. All right, hole or a well. Whatever. Okay, so what else do we know? Which means that the positive charge placed here is going to move from a high potential region towards the low potential region. And so it's going to roll down, and then it's going to roll down further.
By the same token, the contours on this map give a clear representation of an electric field. These are contours of constant electric potential, and they do represent a terrain that has its ups and downs. When real ground goes up and down, a prudent traveler wants to know about it, because going uphill can be hard work. And exactly the same is true for electric potential. Moving up the incline of potential is hard work. And the steeper it is, the harder it is to climb. Of course, if the potential isn't changing, it takes no work at all. And if the potential decreases, the field is downhill all the way. In this analogy, electric potential is elevation, and electric field is the downward slope.
Okay, that one is really, really well done. All right, so let's do a quick derivation. Once again, the only thing you're interested in is the end result. All right, so electric field is generated by a positive charge. Just want to know the potential due to this electric field, due to this positive charge at point P. Okay, so I'm going to place a touch charge right there. Electric field acting on the touch charge is going to induce a force on it in that direction. It's a positive charge. All right, so which means that in the direction of the electric field, the voltage or potential of this charge is going to diminish. That's what it means. Oh my God, this is awesome. All right, so the electric field due to this charge, which is a point charge, is given by this equation. So we'll do it by substitution. Okay, one of the things that I'm going to mention, if you're a physicist, you will love these derivations. as much as I try to avoid these derivations, being a physicist, this is how we come up with the idea. But this is how we express ideas. Okay. So the electric field acting on the charge is pointing in the direction of decreasing potential. That's how you start. And this electric field due to a point charge to your back substitution, this is what you end up getting. So we will take a look at the potential difference between this point and God knows where this charge is going to end up, so that we can come up with an expression for a point potential due to a point charge. Okay, so this is actually cute. All right, so this point charge, evidently we place it right next to this one. This test charge was placed right next to this point charge. So this is going to be the initial, this is the initial location of the point charge right here. And then this point charge is going to go from this point to God knows where else. Okay, so the final location is going to be here. Okay, so don't forget that there's a square here. Okay, and then obviously you do the integral between those two limits. Negative times negative is going to be positive, so that goes away. All right, so it's evaluated at these two different limits. Integral is evaluated. Okay, so one of the expressions is you're allowed to define the potential of voltage is the same from a gravitational perspective. It's the same as height, elevation, right? So the elevation can be described in terms of a reference point. Okay. Are you interested in your elevation with respect to the road? Are you interested in your elevation with respect to are you interested in your elevation with respect to center of the earth? Okay, so you can define zero potential or reference point with respect to anything you want. So what I'm doing is I'm going to assume that this charge is going to be taken all the way out to infinity, and I will assume that at infinity the potential is going to be zero. All right, so this is known as zero. Okay, so all of a sudden instead of talking about voltage or potential, now we're talking about instead of talking about voltage or potential difference, now we're talking about potential of voltage. All right, so this is known as the voltage due to a point charge. Okay, so this expression represents the voltage or potential due to a point charge. Okay, so K is the strength of the electrostatic force. And the meaning of this equation is the voltage is going to diminish inversely with the distance. All right, so this is the expression that we end up getting. So closer you get near the positive charge, larger the voltage is, which means that the more energy is going to be stored within that region. Further away you get from the charge, the positive charge, the less energy is going to be stored within that region. All right, so this is the equation we're using for a point charge. How we came up with this expression is not as important for you guys. All right, what's important is the meaning of the equation and when to use it. All right, so the voltage represents the amount of energy stored within the electric field of a point charge that you're looking at. All right, so I got the best answer for this one. Okay, so basically the potential due to a point charge is going to be V. If you double the charge, what happens to the voltage is going to go by twice. That's it. All right, so if you have multiple charges around, how do you find the potential due to multiple charges? So you got all these positive charges, and then I'm interested in the potential, say, at some points away at this point, right? So what you need to do is just sum up all the charges and their relative distances to that point. That's it. So it's going to give you the total potential within that region. All right, so that represents the amount of energy stored within the electric field, right? Okay, so problem number 6 is the one that I'm interested in. This problem is important. All right, so once again, we're going back to the hydrogen atom problem. And then the only thing that I'm interested in is the ionization energy of the hydrogen atom. What is the ionization energy of the hydrogen atom? So you know that the electron is going to be half an angstrom away. We kind of did a calculation before we found out that this electron would be moving about 5 million miles per hour. So I broke the problem into pieces. I'm not interested in breaking it into 3 different pieces. The only question I have is, what is the ionization energy of the hydrogen atom and how do you solve this problem? Okay, so this is one of those standard problems. Okay, guys, when you're studying for the test, I want you to take a look at this problem. So this is problem number 6 from the handout. All right, so this is the problem number 6 from the handout. So the radius, the size of the hydrogen atom is given. Okay, so it's 10 to minus 11, 5.29. I'll express it in terms of 10 to minus 10. The reason why I'm expressing it in terms of 10 to minus 10, because 10 to minus 10 is known as angstrom. So that's the unit that we use in atomic physics. So the ionization energy expressed in terms of joules. In modern physics, we use electron volts. Okay, so we'll have to do a conversion to electron volts for that one. All right, so you got a negative charge electron moving about a positive charge proton. Both of them are unit charges. Okay, so these are the values of those unit charges. Okay, so the electron is going to have mass. The measured mass of the electron is this number. It's a small number. All right, so the question is, what is the ionization energy that we're looking at? So the ionization energy is what we're interested in. Okay, let's get back to the ionization. Ionization is stripping electrons from atoms. Ionization energy is the energy required to strip or liberate an electron from an atom. So how do you compute the ionization energy of the electron that we're looking at? All right, the answer to that question is this. Let's figure out the energy of the atom at this point. Let's figure out the energy of the electron at this point. Okay, so it's a couple of things about the electron. Number one, it's moving, so it's got kinetic energy. Number two, it's near a positive charge, so it's got potential energy. Okay, so what do we know about the electron? It's got kinetic and potential energy, so which means it's got mechanical energy. Okay, we know it's got mechanical energy because the electrostatic force is a conservative force field. So it's got mechanical energy. It's got a certain amount of mechanical energy. So what we need to do is we need to figure out its mechanical energy. And in order to free this electron from this atom, we need to supply this atom with that amount of energy in order to liberate it. So this electron, whatever its mechanical energy is, that's the amount of energy that we need to supply it with in order to liberate it from this atom. That's known as the ionization energy. So the ionization energy in this case is the same as the mechanical energy of this charge that we're looking at. Okay, so I end up doing a fancy E, not to be confused by the strength of the electric field. I mean, this means mechanical energy. That's what I mean. Right? Because if I keep using capital E for everything, everything gets really confusing. Mechanical energy is going to be conserved. All right, so whatever the mechanical energy this has, it's a combination of kinetic and potential energies. If I give atom this amount of mechanical energy, it's going to give up its electron. That's what it means. That becomes the ionization energy. So mechanical energy of this electron becomes the ionization energy of the atom. All right, so what do we know? The ionization energy is the same as kinetic and potential energies. What do we know? Kinetic energy is the same as this 1/2 mv squared. And potential energy of the electron is potential due to a point charge, which is the proton. So this is the potential of the proton. And obviously electron within this potential, within the potential of the electron. So which means this is potential due to the proton, and this is the charge of the electron. Due to this potential, when you place an electron in it, it becomes energized, and that's got potential energy. Okay, well, it took a while to explain it. All right, so now we got the ionization energy of the electron that we're looking at. This is the mechanical energy of the electron. Okay, so this voltage that you're looking at is due to the proton, which happens to be a point charge. So it's going to give you positive voltage. So this is positive voltage. Do a back substitution right there. And then, okay, all right, so, and then this is the expression that we end up getting. All right, so E times E, K divided by R. Okay, that's fine now. I don't know what I changed, but let's just go back. Okay, so I'm pulling down the numbers. I'm checking to see what we got. Okay, so electron and proton, one of them is negative, one of them is positive, so this is going to be negative as a result. Okay, you don't use the absolute values for these ones because obviously you can have negative and positive voltage, and so obviously in this case, you can have positive or negative potential energy as well. All right, so we got the mass of an electron. Okay, so we got an expression for the radius. Okay, only way we're going to be able to solve this problem is if we can figure out the speed of this electron. All right, so how do we do the speed of this electron? All right, so the speed of this electron, we do it exactly the same way as we did it before. Look at the motion, it's circular motion, which means that there's an electrostatic force acting between these two. Electrostatic force is the centrifugal force. Here's your generic centrifugal force equation. Here's your electrostatic force equation. So equate those to each other. Solve for V. Okay, and then at that point, instead of just, I mean, you can solve it any way you want. Except I decided to employ a trick. Okay, so we need this R and square will cancel. And notice that you have an expression here, which is 1/2 mv squared. And we're looking for V, expression for V. This mv squared is already located here. So if I divide both sides by 1/2, this becomes the kinetic energy term. Okay, so this kinetic energy is the same as half the potential energy of that we came up with. So I'll do a back substitution. I'll substitute this into that equation. All right, and then you get a common denominator between those two, and then you simplify it, and this is the expression that we come up with. Okay, guys, when you plug the numbers in, it's going to give you that number. And if I notice that there's an E squared, right, so which means that E gets multiplied by itself. So I'm going to divide this term just like that. This KE divided by R is the same as the voltage term. So this is going to have units of volts. And I'm going to use E as okay, so what I'm saying here is I'm going to keep E outside and I'm going to use it as a unit. So this KE divided by 2R is going to be 13.58 volts. And then if I use this as an expression as a unit, this becomes 13.58 electron volts. Or you could have just plugged in the numbers and you would have come up with an expression for joules, and then you would have just converted into electron volts, and that's what you would have come up with. Okay, we're slightly over time. I just want to finish this up. Okay, so either you would do it in a weird sort of way that I did it, or you would have just computed a number, get something in terms of joules, and then convert it to electron volts using this expression. Either way, it works out. All right. The next question is, the number is negative. What's the meaning of it? Okay, so the ionization energy is negative. The reason why the ionization energy is negative is because the negative voltage, negative potential energy is going to be larger. Negative voltage, negative potential energy is larger than the kinetic energy, which means that the charge, in this case, the electron, is in a potential well, which means that it's captured by an atom. You end up getting a term like that. This is the potential. All right, this is the potential energy term. So potential energy is negative in this case. This implies that this is a well, and electron does not have large enough kinetic energy to free itself from that well, in essence. So it's got kind of a weird interpretation. Just want to move on to something else.
Lightning. It is one of nature's most awesome forces, yet much remains to be understood. It is still one of nature's great mysteries. Just how are these magnificent electrical discharges created inside clouds? And can their deadly strikes be predicted or controlled? There is much at stake. Each year, lightning causes millions of dollars in damage and accounts, on average, for more loss of life than hurricanes and tornadoes put together. Often seen as the anger of the gods, lightning has humbled humanity for millennia. The gods Zeus and Jupiter were said to demonstrate their displeasure by throwing lightning bolts at the earth. So awed were the Romans that temples were often built on the sites of past lightning strikes. During the flowering of modern science in the 1700s, American founding father Benjamin Franklin pioneered lightning research. Today, many questions remain unanswered.
We're still not sure how it is that lightning begins in the cloud, or exactly what factors control whether the discharge stays in the cloud or goes from the cloud to the ground.
Dr. Philip Kreider is one of the world's foremost authorities on lightning.
Basically, you have a thundercloud with a positive charge sitting in the upper region, negative charge at lower altitude in the central region of the cloud. And the separation of those two charges creates a potential, a voltage of several hundred million volts.
These oppositely charged regions of the cloud are highly unstable and very attracted to each other. A lightning discharge is in some ways like a gigantic version of a common static electrical shock. When these sparks occur within the cloud, they are called intra-cloud lightning. When the negative charge in one cloud flows to the positive charge in another, the result is cloud-to-cloud discharge. Sometimes the negative charge in the ground, especially in tall structures, will jump directly to the positive charge in the top of the cloud. But the deadliest discharges are cloud-to-ground strikes. The Earth has a slightly negative charge, but the powerful negative charges at the base of the storm clouds repel the negative charge, causing the ground to become positive. When the attraction between these charges becomes strong enough, there is a spark.
The peak impulse power being dissipated at the very beginning of a lightning stroke is about 10,000 megawatts, comparable to what the entire city of Los Angeles would consume continually on a daily basis. Thunderstorms are very remarkable, very dramatic, hostile environments. They occur when the atmosphere is unstable, when the atmosphere gets cold real fast. As you go up in altitude, the updraft speeds can approach or even exceed 100 miles an hour.
Out of this hostile environment of changing temperature, electrical charge, and air currents come some remarkable types of discharges. One of them is dendrite lightning, also known as finger or spider lightning because of its delicate discharge pattern. Why this mysterious form of lightning travels along the base of the storm, sometimes for hundreds of miles instead of striking down to the ground, is not understood. For decades, scientists struggled to tame the unpredictable and destructive forces of lightning in order to study it in a controllable manner. The result was an entirely new kind of discharge, triggered lightning. Langmuir Labs, high above Socorro, New Mexico, is a lightning lab in the clouds, a place uniquely suited for triggering lightning. Here, Professor Charles Moore has been studying lightning phenomena for almost 40 years.
We have students here that have gotten to be quite proficient in triggering lightning, initiating lightning by firing these small rockets that we have here up into the air beneath the cloud, pulling a wire, a grounded wire, and this intensifies the electric field at the tip of the wire so much that lightning actually initiates off the tip of the wire and races on up into the cloud. It's just, we call it triggered lightning, but really it's initiated lightning.
The lightning is triggered when a toy rocket pulls the positive ground charge up into a cloud at just the right moment, seconds before the cloud is ready to unleash a lightning bolt.
The rockets that we use are very small and inexpensive, and they're essentially expended whenever they're flown. The wire that is pulled up first gets melted, and then it gets vaporized, and so there's a very strong bar of light. It looks for all the world like a bar of light from Star Wars.
By triggering strikes above sophisticated sensing devices, Moore and his colleagues hope to increase our knowledge about lightning currents, temperatures, and discharge patterns.
Lightning itself is a very dangerous phenomenon. Their energy equivalent to about 2 tons of TNT released in a discharge. But here on the mountaintop, we have an underground steel room. We call it the Iron Kiva, in which we constructed to study lightning. And inside it, we're quite safe when we have lightning strike.
Okay, so this was a nice summary of everything that we've done up to this point. All right. They're safe inside, right? Why are they safe? Because they're inside a metallic enclosure. That's the reason. Right? Net charge is going to remain outside. So what's the net charge on the inside if that's the case? Nothing. Right? There's no net charge on the inside. Only the outside region is charged up, and there's no net charge on the inside. There's no electric field on the inside. There's no net charge on the inside. We did the Gaussian law, obviously, and then obviously net charge within a Gaussian region is going to be responsible for the electric field. And there's no net charge within that metallic enclosure. There's no electric field within it. Absence of an electric field means that there's absolutely zero risk for you to get shocked, because for you to get shocked, the charges should be moving in the same direction. All right, there's no force acting on the charges, whatever the charges may be on the inside. There's just absolutely no force acting on it. All right, so now I guess
in Glenview, high winds took down a power line, trapping a woman inside her car. Police did not know if the wire was live, so they ordered the woman to stay inside the car to avoid contact with the ground. Then
this one is going to be real easy.
They shut down the entire interstate.
It's a metallic enclosure, guys. The net charge is outside. There's no net charge on the inside. What's the voltage and potential difference between inside and outside of this car? Okay, guys, the voltage and potential difference says one region is getting positive charge, the other region is getting negative charge. That's what it means. Outside is charged, inside, there's no net charge on the inside. So what is the potential difference between inside and the outside of a car, if that's the case? So the excess charge is going to be on the outside. If that's the case, this is going to be really complicated. So you got this metallic enclosure, so it's the hollow conductor that you're looking at. The net charge is going to be on the right at the surface, so there's going to be a voltage right at the surface. All right, so what's the voltage and potential difference between inside and outside? What's the electric field on the inside? There's no electric field between inside and outside of it. All right, so which means that the electric field on the inside is going to be 0. If the electric field on the inside is 0, look, potential difference, meaning that there's going to be an electric field pointing from a positive charge region towards a negative charge region. There's no positive or negative charge region inside of it. All right, so the electric field is going to be 0, which means that there's absolutely no potential difference between inside and outside of a metallic hollow conductor. All right, so there's no potential difference between inside and outside of a metallic enclosure. That's what it means, which means that the entire thing is an equal potential. Whatever the voltage and potential at the surface is exactly the same on the inside. There's no potential difference. There's no electric field. You would not get shot by touching the outside of a car. That's what it means. All right, so whatever the surface potential is, it's the same on the inside. There's no voltage or potential difference. Hence the reason why you're going to be fine. All right, so the entire structure of the car, if you're on the inside, whatever the voltage at the surface is, it's going to be the same as the inside. And then when you start to move away from the source, in this case the car, the voltage is going to gradually decrease. That's what it means. No electric field within a metallic enclosure, the charges will be right at the surface. And then as you start to move away, the strength of the electric field is going to diminish. All right. I pick out the best answer. I know which one you guys will pick. All right, so what do we know? We have a hollow metal sphere charged to a potential V. So what's the potential at its center? All right, so most of you guys will pick B, despite the fact that the A is the best answer, right? Guys, there's no potential difference between outside and inside of a metallic enclosure. Whatever the potential at the surface is, it's going to be the same with that. That's what it means. No potential difference. Hence the reason why you're not going to get shot. Hence the reason why you can touch the outside of the car, you're still fine. All right, so despite the fact that you guys this stuff is new to you, this is actually a common knowledge.
Hello? Sorry, my meeting ran late. I should be home in about a half an hour.
Sure, I can pick up dinner. What do you want? Hot and spicy. That's what I'm talking about. I will. I love you too. Whoa. Oh, man. So that's what an airbag feels like. My car. Great. I should probably get out and see how bad the damage is. Wait. Are those telephone wires or power lines? Either way, they could be hot. No way to be sure. Don't take any chances. Just stay in the car and call 911. Good thing I actually paid attention during that safety meeting. Hi, this is Stephen Stonebanks. I've been in a car accident. I hit a power pole. I'm on Highway 18, somewhere east of the 356th Street exit, a couple of miles. No, I'm okay, but there are power lines on my car. Okay, yeah, I know. I won't move until you tell me that the line is de-energized. Yes, I will stay put. Okay, please hurry. Thank you. Honey? Listen, I've been in an accident. No, I'm fine. I hit a power pole. The car is a mess, but I'm okay. Yeah, I've called 911. They're on their way. Oh, no. Hey!
Are you okay?
Hey, stay back! No, don't come any closer. You could get shocked by the ground around these down power lines. Stay back about 35 feet and make sure no one else comes near.
Okay.
I've called 911. They're on their way. Thank you. Honey? No, I'm fine. No, don't worry. Yeah, the police are on their way. Yeah, all I've got to do now is sit and wait. Honey? I gotta call you back in a couple of minutes. Oh boy, not good.
Oh my gosh.
Okay. Plan B. Exit the vehicle. But now I gotta worry about touch potential. Touch potential is risk of electrocution based on one part of the body touching an energized object like a car while simultaneously touching the ground. Electricity flows from the vehicle through the body and into the ground, essentially making me into a human jumper cable, which would be bad. I gotta jump and land with both feet together. Whew! Okay, now step potential. Because the ground is energized, electrical current can travel through me if my feet aren't close together. Electrical current enters through one foot, out the other. The further apart my feet are, the greater my chances of getting shocked. So I must move away using short, shuffling steps. Shuffle, shuffle, shuffle. There you go. You got this, Stephen. No large steps. Just keep on shuffling. Every day I'm shuffling. Oh. I'm sorry, I can't come to the phone right now. I'm busy trying to stay alive at the moment. Almost there. Hi, honey. No, everything's okay. No, nobody got hurt today. Well, except the, Remember how we were talking about getting me a new car? Telephone wires or...
All right, so there's a couple of things that we need to emphasize. Notice that he's going to be able to touch you cannot touch the car and the ground at the same time. There's going to be a huge potential difference. All right, so this is known as the touch potential. Contact points are at two different surfaces. All right, this car is electrified. Ground is also electrified, but they're not at the same voltage or potential. There's a large enough potential difference, which means that there's going to be electric field pointing from high voltage, high potential towards low potential. Charge region is considered to be high potential. Electric field is going to force the charges to go through your body, which means that you will get shocked. That's what it means. All right, so that's what it is. Okay, you can touch the outside of the car, you're fine. You can touch the outside metal of the car, you're fine. No potential difference between the car, inside of the car and the outside of the car. It's an equal potential, the entire structure is. All right, so the best thing to do is jump away. Obviously, you cannot touch the ground and the car at the same time. And after you jump away, you cannot walk. All right, so the ground is energized, which means that the car is going to act like the source of potential. High voltage potential is going to be the car. And that there's going to be a potential difference as you start to move away from the car. All right, so as you start to move away from the car, the voltage and potential is going to diminish. So if there's potential difference between the contact points, the charges are going to be forced to go through your body, which means that you're going to get shocked. All right, so this is known as the step potential. You can't do that. All right, larger the difference between the step sizes, as the larger the voltage and potential difference is going to be. It's almost like this region is not positive charge. This is like negatively charged. All right, remember, larger the separation distances between two charged regions, the larger the voltage and potential differences, the more energized the charges will become, which means that they will do more damage. So this is your step potential. So the best thing to do is keep your feet together next to each other. All right, so they will be almost at the same potential. So you said you could shuffle, obviously. This is one way of doing it. That's not the way of doing it. There's a second way of doing it. I think this one is also going to do a good job.
Stay safely out of our way. But sometimes storms or accidents can knock down lines. If a power line falls across your car, do you know what to do? If your car is still drivable, simply pull out from under the wire. If your car is disabled, the most important thing to do is to stay inside. Use your cell phone to call for help. Keep others. Sometimes storms or accidents falls across your car, do you know what to do? If your car is still drivable, simply
okay, yeah, just drive through. There's no reason for you to stop.
Pull out from under the wire. If your car is disabled, the most important thing
I don't know why people do that.
Use your cell phone to call for help. Keep others away from the car. Only get out when utility workers tell you it's safe. Never touch the car and the ground at the same time. The only time you should get out is if there's imminent danger, like fire. Open the door fully. Do not step out. Stand on the metal framing of the car. Keep your hands close to your body to avoid touching the car and the ground at the same time.
And then you jump.
Slide your feet together. Hop off with both feet. Hop away from the car, keeping your feet together.
And then you can hop.
Framing of the car. Time. Slide your feet together. Hop off with both feet. Hop away from the car, keeping.
One thing that I don't like about it is if you lose your balance and if you fall, top of your body is not going to be at the same potential as the lower portion of your body. You will get shocked. All right, falling is a horrible idea. So if you're not a very balanced person, just shuffle.
If you feel a tingle, put your feet back together and hop further away.
Yeah, if there's any sort of tingling, which means that there's still a potential difference, large enough potential difference for you to feel anything. So just pull your legs in. All right. Let's just finish up this portion of the lecture. All right. So what else do we have? The spark occurs at a given distance, a certain distance, which means that the charges will have enough energy to jump that gap. So which means that the voltage and potential difference is going to be just enough at that distance to energize the charges to jump the gap. That's what it means. It's recommended that people avoid high grounds during thunderstorms because the charges will require enough energy to jump a shorter distance sooner than the longer distance. So it's more than likely it's going to strike high ground. All right. If taller objects and structures are more likely to be struck by lightning, why then the Sears Tower? I'm talking about the one in Chicago. It's not the one that gets struck by lightning 100% of the time, because it depends on the charge distribution. All right, the charges under the clouds and underground are not uniformly distributed. Right? So sometimes the charge distribution is such that you will have a stronger, higher charge density for a distance which is larger than a shorter distance. Okay, so we discussed that before, so go back to that discussion. All right, if there's a down, like power line touching the metal of the car, is it possible to touch the outside of the vehicle without getting electrocuted? If you're a passenger inside the vehicle, 100% of the time, you can touch the outside of the car, the metal of the car. As long as you're sitting on the inside, you can do that because there's absolutely no potential difference between inside and outside of the car. Okay, so the question is, how come there's no potential difference? There's no potential difference because the outside of the car is going to be charged, the inside there's no net charge. Potential difference means that one region is getting positive charge, the other region is going to be negative charge. There's no net charge on the inside, guys, so there's no electric field on the inside, which means that the inside and the outside of a hollow conductor or metallic enclosure is going to be at the same voltage or potential. So there's absolutely no way you could get shocked under the circumstances. All right, so we discussed that. All right, so let's move forward. All right, so let's get into the mathematics of it. More sophisticated problems at this point. I'm going to give you guys a few problems to focus on. Let me just check to see which chapter this is in. All right, so this is lecture review. But, all right, so potential due to line charge. Yeah. Potential due to line charge. Let's go back. All right, so this is going to be a case study. Okay, so we'll have an electric potential due to a continuous charge distribution of a line charge. All right, this is a simple enough example. So this thing is going to be charged up. It's going to be a line charge. And we're going to be interested in the potential at point P. All right, so what is the potential at P? That's what it means. So I'm just going to move it here so that our geometry is easier because this is just an example. So this point is separated from the line charge through a distance of D. And this line charge has a length which is going to be L. So we're measuring the length along the x direction. And then we're going to be looking at the potential due to the differential charge element that we're looking at, which means that you just sum up all the charges here, check to see what the potential due to these charges at that point is, and then just sum up the potential due to every single charge across this line. So we end up grabbing a very small number of charges, and we're checking to see the potential due to these charges at that point. And then we will keep doing it for every single charge that we have across this length. All right, so this is going to be R. Notice that we end up creating ourselves a triangle. All right, so we're just going to sum up the individual charges, obviously, along this length. So we will grab a small portion of it. So dq means a very small portion of the charges, and we'll check to see what happens to the potential. And then what we will do is we will just sum up the effect of these charges at point P, their contributions to potential at point P. All right, we are going to take a look at the distribution of these charges, and we will express that distribution along the x direction using a linear charge density. So the net charge per length is going to be the linear charge density that we got. All right, if you don't express it in terms of if you don't express this distribution of this charge in terms of a linear charge density, you cannot do the mathematics in essence. So the reason is more mathematical than from a physics perspective, because the ideas need to be expressed in terms of math in physics. So the best thing to do is obviously we have to add up, sum up all the charges on the x direction. So why not just express the charges in terms of charge density? That's the whole idea. All right, so the constants are the ones that you have to pull in front of the integral sign. All right, so you got dx divided by r, okay, and then r is going to change with distance on the x direction. Okay, so when you slide this way and that way, when you slide it this way, r is going to be longer. When you slide it this way, r is going to be shorter. So the r is going to be a function of x, so which means that we have to come up with an expression for r. It's going to be expressed in terms of x. All right, so the x is going to locate the charge for charges here, and obviously we will slide x from this point all the way to that point, and look at the contribution of the charges to the potential at point P. All right, so this becomes a small triangle. All right, so we end up, this is the hypotenuse, height, the base. All right, so Pythagorean theorem is what we get to use for that. All right, so r expressed in terms of the Pythagorean theorem, and notice that now in the denominator we got our x. All right, so our variable becomes x. Okay, so how do you do an integral like that? I don't care. Basically, this is not a course in math. You can look it up if that's what you want to do. If you know how to use MATLAB, use it. If you have a calculator, if you don't, just get a calculator. It can do the integral calculations for you, but when you do it, this is the expression that you come up with. And that's it. So this becomes the answer. And then what you need to do is you need to evaluate it at the limits. All right, so we're going from 0 to L. All right, so every time you see x, plug in L, and then minus every time you see x, just put 0 in, and this is the expression that we end up coming up with. Ln, this expression minus ln that expression. So this expression, if you factor out natural log, this becomes the denominator. And that's it. So that's as far as you go. In reality, you would take it one step further. They usually want you to express the final voltage or potential in terms of the net charge, not in terms of a charge density. But I just wanted to illustrate the mathematics. Okay, so this brings us to the next point. We've done this before. Okay, why is it that I'm not hearing this? Okay, I'm fine with that. Remember, we were looking for the strength of the electric field due to a uniform charged ring. And then we end up doing quite a bit of algebra. So I'm just going to jump around. This was the first chapter that we covered. And this was a lot of work in reality. All right. It's about 2.5 minutes long. Actual derivation, when done in class, this thing takes about 30 minutes to 40 minutes. This thing is long. Okay. So mathematically, this thing takes a while. The only thing I want you to realize is, number one, this is a lot of work. And number two, when we were done with it, this is the formula that we came up with. So this is the strength of the electric field along the z direction. All right, so here we end up using vector calculus, and we end up doing quite a bit of work in order to solve this one. Okay, so we'll get to do the same problem, except we will get to do it slightly differently. All right, so the first thing we will do is we'll do the potential. All right, so if you're dealing with potential, it's much easier because we don't have to worry about the vectors. All right, so potential is a scalar, yeah, so we don't have to worry about vectors. So what we will do is we will find the potential due to a circular line charge at this point, which is P. All right, so you can get a single charge, and then obviously you can grab a bunch of them, small portion of it, and then check to see how much this is going to influence the potential at that point. All right, and then you have to set up your XYZ coordinate system. So this P is going to be along the vertical direction. Capital R represents the radius of the circle. Lowercase r is going to represent the distance between the charge and that point, charge distribution at that point. Okay, so for a single charge, it's going to give you the voltage potential at that point. If you have two charges, what do? You just add up their contributions. If you have three charges, add up their contributions or whatever. So that's what we're going to do. So now we are adding the contributions to a number of charges within this small region. And then obviously they're going to be contributing to the region. The voltage at this point, so the more charges you grab, the more the voltage and potential is going to change. So that's what it means. All right. And now what we will do is obviously we will express the net charge in terms of charge density for mathematical reasons. All right, so it's the line charge density per, this is the net charge per length multiplied by the arc length that you're looking at. All right, so ds is going to represent the arc length in this case. All right, so the arc length is going to, when you do the computation, it's going to give us the circumference. So I'm just going to do a lazy thing. First thing I'm going to do is compute r. Once again, this is going to be the hypotenuse. Z squared plus r squared divided by the square root. Now I'll do a back substitution. R is not going to change, Z is not going to change. So these are constants, so you can just pull them out of the integral sign. So those are constants, so it's not going to matter. Not going to affect computation. ds, the arc length, when you sum them up, it's going to give you the circumference. So that's going to be 2 pi r. And now we came up with an expression for the voltage of a circular line charge at point P. That's it. Okay, so what can you do with it, which is really interesting. All right, this is a lot of work. This is actually half a page of computation. I'm just explaining everything. That's the reason why it looks like it's a lot of work. What you can do with that is you can, by using that, you can actually figure out the electric field. All right, you can do one more step, and then the stuff that took me 30 minutes to calculate, I could do within 5 minutes. All right, so that's what I'm going to show you how to do. So this is calculating potential from E. Actually, I meant to say calculating the electric field from potential. All right, so I just got the terminology wrong, but that's fine. All right, so these are equal potentials. Electric field is pointing in the direction of the diminishing potential. It's coming at an angle. All right, so the electric field is generated by this net charge or point charge or whatever. And so this is a dot product, which means that the electric field does not need to be in the same direction, but only the component of the electric field going the radial direction is going to point in the direction of the diminishing voltage and potential. So that's what it means. So when you see an expression like that, there's a story behind it. Make sure you see the physics behind it as well. All right, so this is a dot product, which means that we're interested in the component of the electric field along the radial direction. The component of the electric field along the radial direction is going to be the cosine of the angle between R and E. So that's the meaning of the dot product right there. And so I'm continuing with the derivation. All right, so I'm just going to isolate E on the left-hand side. So that's what I'm going for. And so I'm dividing both sides by GR. And then E times the cosine of the angle represents the radial component of the electric field. That's what it means. Now I came up with an expression for the radial component. All right, so what that means is if I know the voltage, and if I differentiate voltage along the radial direction, I can figure out the strength of the electric field along the radial direction. All right, so this is a generic expression. What that means is I can actually generalize this expression. I can say, oh, if I know the voltage, I can differentiate voltage along any direction I want and check to see what the strength of the electric field along that direction is. I can differentiate voltage along the x direction. It's going to give me the strength of the electric field along the x direction. All right, guys, if you've never seen these notations before, here's your introduction. These are known as partial derivatives. All right, so partial derivative means that you can take the derivative of anything along the direction that you want. Okay, so if you check to see how the voltage is changing along the x direction, and so changing voltage along the x direction is going to be due to the electric field pointing in that direction. You can look at the changing voltage along the y direction, so that's going to give you the strength of the electric field along that direction. You can look at the changing voltage along the z direction, so it's going to give you the direction of the electric field in that direction. All right, back out of it a little bit. Electric field is going to point along the x direction in the direction of diminishing voltage. Along the y direction, once again, it's going to point in the diminishing of voltage on the y direction, and it's also going to point in the direction of diminishing voltage along the z direction. All of a sudden, you've got the components of electric fields along the x, y, z directions or any direction that you want. All right, this is a really powerful mathematical method because voltage, I don't care what charge distribution you may be looking at, is very easy to compute. And then by taking the derivative along any direction that you want, you can figure out what the strength of the electric field is along that direction. All right, so this is a powerful mathematical technique. All right, so remember this is the equation that we came up with for the voltage of a circular charge density, circular charge ring. Okay. All right, so what I'm going to do is by taking the derivative along the z direction, I'm going to come up with exactly the same equation that I came up with during the first week, while we were in the first chapter. Except we'll check to see if there's a negative sign that we missed. All right, so it says if you find the voltage, which we knew how to do for a charge ring, now we can just do one more step of computation and figure out the strength of the electric field and check to see if we can recover this equation using a method which is much more powerful. More powerful meaning that it's easier to compute, so you reduces the chances of making a mistake. All right, so this is our voltage. So I want to express this using the net charge. All right, so this represents the charge density, linear charge density. That's the net charge per unit length multiplied by the length. 2 pi r represents the circumference. So when these two multiply, it's going to give you the net charge. So I do a back substitution. All right, so I got an expression for the voltage for a charge ring. All right, now what I'm going to do is I'm going to express this equation as this equation. All right, so this is just before the lecture, I was just doing this, and I was also babysitting, obviously. So this should be -1/2. Okay, so I'm going to go back and make a correction shortly. I got distracted a little bit. And then the only thing I have to do is just take the derivative of this on the z direction. All right, so which means that this expression needs to be differentiated on the z direction. And then, all right, so which means that this expression is the one that I'm going to evaluate. All right, so I caught on. Notice that this reflexively on u was going to be 1/2 because this is the denominator correction. All right. So partial derivative is the same as an actual derivative, except now you pick and choose which direction you want to do the evaluation. So obviously we got the z direction that we're interested in. All right, so how do you take the derivative of this? So what happens, you have to drop this in front of it. So it's going to be 1/2, and then you have to subtract 1 from it. All right, so this is going to give us 3/2. And then obviously we're differentiating everything with respect to z. Now you have to take the derivative of z, so it's going to be 2 times z. All right, so that's the expression that we got. So you have 2 here, you got 2 there. They will cancel. All right, now this expression needs to get substitute back into that one. All right, so this is -3/2, so this is the denominator, that's the meaning of it. And then we have a negative here, so if you take the negative out of this derivative with respect to z, partial derivative, it's going to give us this strength of the electric field on the z direction. So we have negative and negative, so it's going to give us a positive. And that's it. Okay, so this was the equation that we came up with. Believe it or not, guys, the work is much less than the amount of work it takes to do this at most 10 minutes, as opposed to spending half hour. So there's no negative sign here. And we didn't have a negative sign before either. All right, so, and then we came up with the same equation. All right, so as part of your homework, you'll get to do the same thing using a charge disk. All right. All right, so let me check to see how long this is. This is like 2 minutes long, and we end up doing a lot of calculus in order to do this. All right, so we have to figure out what the charge was, and then we end up using the electric field due to a point charge, and then we end up all those point charges, the direction mattered, because the direction mattered, obviously, there was an angle here, which was theta, and there's going to be an angle here, which is going to be theta. All right, so I'm not, just take a look at the complication of this. The direction matters, the angles matter. You have to keep track of the directions. You have these cosines of the angles, and then you have to interpret it. So the math gets fairly intense. So what you will have to do, and this could become your test potentially, this could be a nice test question. I want you to find the potential at point P, all right, which is going to be fairly easy to do. And then I want you to figure out the electric field by taking the derivative of that on the z direction. All right, maybe these are standard questions, the test questions, so I want you guys to focus on that. All right, so let's back out of this real fast.